Hi everyone, welcome back to my YouTube channel. I am Reeti and I'm back with another lecture in the DBMS series. So in the last couple of lectures we learned about normalization, types of normalization and much more things. In this particular video we are starting with a very new topic, that is transaction and concurrency control in DBMS. So without any further ado, let's get started. Now the word transaction may be familiar to many of you. Consider that I want to transfer some money to my friend, and once the payment is successful, I often get the message as transaction is successful. Consider that I am ordering something online, and once the payment is successful here, again I get the message as transaction is successful. So you can understand it in this way, that transaction is basically a collection or combination of some database operations like read, write, commit, rollback, which is used to perform a specific task. So transaction is a logical unit of work that comprises of one or more database operations like read, write, commit, rollback to perform that particular unit of work. So consider there is a person A who wants to transfer 50 rupees to person B. So this is a transaction which is happening here. Now transaction have read as well as write operations, and then there are commit and rollback. So we will be learning about commit and rollback in next set of slides, but let's learn about read and write operation. So a read operation involves retrieving or fetching the data from the database. So whenever we are retrieving or fetching some values from the database, we call it as read operation. It is often denoted by R. Now coming to write operation. So a write operation in transaction involves modifying the data in the database. So whenever we need to modify or update the data in the database, we use this write operation. So it is denoted by W. So let's come back to this example again. Now A wants to transfer 50 rupees to B. So what are the things we need? So first we need what is the current bank balance of A. Consider that if A is having only 20 rupees, would he be able to transfer 50 rupees to B? No. So we need to fetch the current bank balance of A. So first we will do a read operation on A, which is fetching the current bank balance of A from the database. So consider that right now A is having 100 rupees. So we have fetched the current bank balance of A from the database. Now we have to perform this arithmetic operation where we will be deducting 50 rupees from A's current balance. So that would be 100 minus 50. That is 50 rupees. Now A's current balance is 50 rupees. So we have to update this value in our database. But before updating, we need to know that if this particular amount has been transferred to B or not. Consider that we have updated the value of A, but at some point B does not receive 50 rupees. So there will be data inconsistency. So what happens is we do a write operation, we do a modify operation, but this particular write operation goes ahead and update the value 50 in the transaction logs, or you can say a shared memory. So before commit, if there is any operation which happens in a transaction, always go to the transaction log or log records. So this value would be updated in the log records. Now coming to B, again we need to know that what is the current value or current bank balance of B. So we'll do a read operation on B. So it will give me the current bank balance of B, consider 50 rupees. So we have got the current bank balance of B. Now we need to add 50 rupees to B's balance. So we'll do an arithmetic operation. So it will add 50 rupees to current B balance, that is 100 rupees. Now we need to update this value as well in the database. So we will do W of B. This will be W of A. So it will update the value to 100 rupees. Again, this will go ahead and get saved in the transaction logs. We are not saving or updating the value in the database yet. Now we know that all the operations have been successful. The arithmetic operations and everything have been successful. Then we will perform a commit operation. Commit says that if all the operations have been successfully done, then go ahead and update the value in the database. So commit will read everything from the log records, and once log records see the commit, it will go ahead and delete all the log records and it will get updated in the database. So this is how the transaction happens. So here also there is an example. Consider we are using the Swiggy app, we are ordering something, we go to the payment page, we enter the bank details and we get the OTP. There could be two scenarios. One, there is some network issues or failure. Second, there is no network failure. So when there is no network failure, the order is done, the payment is successful and the transaction is complete. But once there is a network failure which is encountered, there could be two cases. One, the amount is deducted from your bank account. Second, the amount is not deducted from your bank account. So there is a rollback which comes into picture, which says that if at any point there is any failure which is encountered in the transaction before commit, what we do is we roll back it to its original state, so that if there is any amount which is deducted, you will get a message that you will be getting credited this particular amount in your bank balance within 7 days or within 24 hours, because that is a rollback step which is applied. So if you are entering your OTP and some amount is deducted from your account, but still the order is not completed or the order is not done, you will get that particular amount back in your bank balance, or you will get that particular amount refunded. So consider an example of a banking application where a customer Ram wants to transfer 100 rupees to Shyam. So let's see all the steps which we discussed here only, but let's see how these steps execute. So the step 1 is we have to begin the transaction. The step 2 is the application will fetch or read the current balance of Ram, since Ram wants to transfer 100 rupees to Shyam. So we'll fetch the current bank balance of Ram. So that would be read of Ram. Now the step 3 is the application will calculate the new balance after the transfer. So that would be current balance of Ram minus 100 rupees. So consider right now Ram is having 200 rupees. So we have to deduct 100 rupees from current bank balance of Ram. That would be 100 rupees. So we have performed the arithmetic operation. Now the step 4 is we have to update it in the temporary storage or transaction logs. That is W of Ram, that is right of Ram. So why we are updating it in the temporary storage or transaction logs? Because consider that if we are deducting something from Ram balance, this particular amount should be transferred to Shyam. If at any point while transferring there is a failure which has happened, so we need to take care that if the transaction is successful, only then go ahead and update in the database. Before that, update it in the transaction log so that we have logs of everything, but we are not updating any inconsistent data in the database. Now the step 5 is the application will fetch and read the current bank balance of Shyam. Then step 6 is the application will calculate the new balance of Shyam after the transfer. Consider Shyam is having 100 rupees. So after the transfer, Shyam is having S plus 100, that is 100 plus 100, that is 200 rupees. Now the step 7 is we have to update it in the temporary storage or transaction log, that is W of Shyam, since we are modifying the data. Now step 8 is if all the updates are successful, at all these steps everything is successful and there was no failure, and there are no errors, commit the transaction to make the changes permanent. So we have to perform a commit operation at the end of transaction so that all the changes are permanent and it's updated in our DB. So it will go ahead and update in our DB. Logs are maintained till the occurrence of commit. After that, log files are deleted and database is updated. So before the commit, all the log files and everything is maintained, but once it encounters commit, it deletes all the log file and it goes ahead and update in the database. Now the step 9 is if an error occurs during any step, roll back the transaction to revert the changes made within the transaction, that is rollback. So consider at any step from step 1 to step 7, there is any issues which we have encountered, or the transaction has failed because of network failures, data failures, or things like that. So what we have to do is we have to perform a rollback so that everything is reverted back to its original state and there is no data inconsistency which is present in our database. So rollback is often introduced whenever we encounter error or any issues at any point of the transaction. So this is all about the steps involved in the transaction. So considering the last example, let's learn about transaction state. So this was the transaction log for the last example. First we begin the transaction, then we read the value from Ram, then we do the arithmetic operation, then we write in Ram, then we read the value of Shyam, we do the arithmetic operation, we update the value of Shyam, then we do commit so that all the data is pushed into the database if everything is successful, and we perform rollback if we encounter any issues still here. So the case 1 is where all the operations are successful and we are updating the data into the database. So the very first step is the active state. So the active state occurs that whenever the transaction is begin and we start performing the database operations, at that particular moment the active state occurs. So here you can see that before commit, whatever is the operation which is being performed, we say it as a partially committed state, because if at this point there is any failure encountered, we roll back the entire transaction, or if at this point there is a success occurred, so we commit the transaction. So we call it as partially committed state. Now coming to commit, so this is a successful state. We can say now we have come to a successful state and now we can update the data into our database. And then after rollback there is a completed state. The transaction is completed. Now coming to case 2 where we encountered some failures during the transaction. So again, when we are reading the value, it's the active state. After the begin statement, whatever operation we are performing is the active state. If before the commit operation, whatever operation is getting performed, if it fails somehow, then we call it as a failed state. And then commit state is called as cancelled or rollback state, because we don't commit, we rather roll back. So if there is any issue which is encountered at this stage, we come to rollback. If not, then we come to commit. So we will cancel or roll back and then the transaction is completed, even though it's failure, but the transaction has been completed. Now we again need to do the transaction. So these are all the states which are involved in a transaction. Let's learn about concurrency control. So concurrency control ensures that multiple transactions can run concurrently without compromising the data consistency. So if there are two transactions T1 and T2, it ensures that T1 and T2 can run concurrently or parallelly without compromising the data consistency. That is, data should be similar for both the transaction. There shouldn't be any data inconsistency. So consider an example where there is a banking system where two transactions are happening concurrently or parallelly. So Ram is giving 100 rupees to Shyam and Shyam is giving 50 rupees to Ram. So the data should be consistent for both the transaction, because if Ram is giving 100 rupees to Shyam, we have to deduct 100 rupees from Ram's current balance. And if Shyam is giving 50 rupees to Ram, we have to deduct 50 rupees from Shyam's bank balance. So these two are happening concurrently and as part of the same values. So we can say that the data should be consistent as part of this concurrency control. So if there are two transactions T1 and T2, and if as part of T1 also we are updating some value, and if part of T2 also we are updating some value, the data should be consistent. It shouldn't be a case that if we are updating some value here, then we are going here and reading the same value and then updating the new value. It shouldn't be the case. The transaction should be isolated of each other. So if there are any concurrent or parallel transaction, that should happen without any hindrance to the data consistency. So there are some techniques which are often used to manage the concurrency control. First is locking, second is two-phase locking, and third is timestamp ordering. So we can use these techniques to manage the concurrency control in our database. Now, what are these ACID properties? So ACID properties are the properties which ensures that the transactions are processed reliably and accurately even in complex situations like system failures or network issues. So if we encounter any complex situations like system failures, network issues while having a transaction, it makes sure that the transaction is accurate and reliable. So ACID properties are the properties which make sure that our transaction is processed reliably and accurately. Now coming to the acronym ACID. So A stands for atomicity, which means that either execute all the operations or none of the operations should be executed. Coming to C, that is consistency, which says that read should fetch up-to-date data and write shouldn't violate any integrity constraints. Now coming to I, that is isolation. So one transaction should be independent of other transaction, that is they should be isolated. Now coming to D, that is durability. So the committed transaction should remain even after a failure or crash. So if we update the value in the database, that should remain even after we fail any failure or crash. So let's learn about each and every in depth. Now coming to A, that is atomicity. So it ensures that a transaction is treated as a single unit of work. Either all operations are completed successfully, that is commit, or none of them are applied, that is rollback. So as I told in the earlier videos as well, that if at any point there is any failure which is encountered in the transaction before the commit, we often perform the rollback, that is we revert back it to its original state. So it says that either all operations should be completed or none of them should be applied. So if there is a transaction, consider there is a transaction begin, we read a value from A, we update the value of A, and then we perform the commit. If at any point here, if the transaction fails because of some network failures or other issues, we have to perform a rollback. So we will perform a rollback and it will go back to its original state. And if at any point there is no failures, then we perform the commit and the data is updated into our DB. So this guarantees that the database remains in a consistent state despite any failures or interruptions during the transaction. It ensures that our database remains in a consistent state, because consider that if I have updated any value into our database and if there are some more operations which are being performed on the same data, then there should be inconsistency which will be present. Now consider an example. So consider Ram is transferring money to Shyam. The transaction must deduct the amount from Ram's account and then add it to Shyam account as a single operation. If at any moment or at any part this transaction fails while transferring amount from Ram to Shyam, example due to insufficient funds, system error, network error, the entire transaction is rolled back, ensuring that none of the account is affected partially. So if there are transaction which is happening between two accounts, Ram and Shyam, and if we are transferring any amount of money from Ram to Shyam, if at any point there is any failure which is encountered, because consider maybe we are transferring 100 rupees to Shyam and Ram's current balance is only 50 rupees. So we are encountering an issue because Ram is having insufficient balance. So we should roll back this transaction and it should come to its original state. So let's learn about consistency. So consistency ensures that first, read operations retrieve consistent and up-to-date data from the database, and second, write operation ensures that the data modification maintain database constraints such as foreign key relationship, unique constraints, so that the data remains accurate. So consistency says that the data should be consistent. Now whenever we are performing any read operation of any of the data, consider we are reading the value of A, so it should show me the up-to-date data, like the last updated value of A should be shown while doing the read operation. And coming to the write operation, so if I'm doing any write operation on the A, so it should ensure that the data modification maintain database constraint. So if there is any constraint which is applied, consider that it is a primary key, so I can't update any duplicate value in it, right? So these constraints should be maintained and these constraints should be taken care while updating any value in the database. So it guarantees that the database remains in a consistent state before and after the execution of each transaction. So it ensures that our database should be in a consistent state before and after execution of any of the transaction. So consider A is transferring 10 rupees to B. So what we need to do, first we'll fetch the current value of A. So the current value of A is, consider, 50 rupees. Now we need to perform the arithmetic operation where we need to deduct 10 rupees from A. So that would be 50 minus 10, that is 40 rupees. So we will write the value of 40 in A. Now we need to fetch the current value of B. So we'll fetch the current value of B, consider 20 rupees. Now we need to update the value of B. So B will be having 10 rupees extra. So that would be 20 plus 10, that is 30 rupees. Now we have to write this particular value in B, that is 30 rupees. So before the transaction, if you see, A was having 50 rupees and B was having 20 rupees. So 50 plus 20 gives us 70. Now after the transaction, if you see, A is having 40 rupees and B is having 30 rupees. If we again do the addition, it is 70. So you can see that data is consistent before as well as after the transaction. So consistency basically ensures that the data should be consistent. If we are reading any value from the database, it should give me an up-to-date value. If I'm writing any value or updating any value in the database, I should follow the integrity constraint so that the value which is being updated is not a wrong value or doesn't violate any of the integrity constraint. Now consider an example. Consider you had 100 rupees in your account, but you want 50 rupees cash. So you transferred 50 rupees to a person X and he gave you 50 rupees cash. Now before the transaction, you are having 100 rupees in your account. Now after the transaction, again you are having 100 rupees, 50 rupees you have in your account and 50 rupees is the cash which you got from the person X. So you can see that the data is consistent before as well as after the transaction. Now coming to I, that is isolation. So it ensures that if there are two transactions, 1 and 2, then the changes made by transaction 1 are not visible to transaction 2 until transaction 1 commits. So if there are two transactions which is happening, consider on the data A only there are two set of transactions happening. So as part of first transaction, we are increasing the value of A by 10, and as part of second transaction, we are decreasing the value of A by 10. So while the transaction is reading the data, the DBMS ensures that the data is consistent and isolated from other transactions. So these two transactions should be isolated from each other. This means that the other transaction cannot modify the data being read by the current transaction. So consider if T1 is the current transaction, T2 can't be performed until or unless T1 is committed or all the operations are done successfully. Only then T2 can go ahead and read the updated value which is being updated here. So until it's committed or rolled back. So if this transaction is committed or if there is any rollback which is performed, we have to wait for this transaction to complete. Only then T2 can go ahead and read the value of A and perform its operation. So here is an example. Consider A is having 40 rupees in the DB. So transaction 1 is updating the value of A to 50 rupees. Transaction 2 is reading, getting or fetching the value of A. So if transaction 1 is committed, according to transaction 2, the value of A would be 50 rupees. As in transaction 1 we are updating the value of A to 50 rupees, so now 40 would be updated to 50, and since this transaction is committed, now T2 can fetch from the current value, that is 50 rupees. Now if transaction 1 is in pending or running state, according to transaction 2 the value of A would be 40 rupees, because still the transaction 1 is not completed. So if we read the value of A, it would be 40 rupees only, because the write operation has not been completed, it's in pending or running state, so the value of A would be 40 rupees. So you can see that there is data inconsistency. That is why it said that if there are two transactions which is happening, we have to wait for one transaction to be completed or committed before starting the second operation, which involves the modifying the same data which transaction 1 is also modifying. So two transactions should be isolated of each other. So let's learn about D, that is durability. So it ensures that once you save your data, that is commit a transaction, it stays saved even if the system crashes or there is a power failure. So consider you saved your data into the database and immediately after that there is a system failure or there is a system crash. That particular data would be saved in your database, that particular data won't be lost. So your data is always safe and won't disappear after you save, as committed transactions are not lost. So if you commit a transaction, that could never be lost even if there is any system failure or any network issue. If your transaction is committed, the data is saved, it's not lost. So most DBMS use a technique called as write ahead logging, that is WAL, to ensure durability. Before modifying the data in the database, the DBMS writes the changes into a transaction log, which is often stored on a disk and in a sequential manner. This ensures that if there is any failure event, the database can recover to a consistent state. So how a transaction takes place? So consider that if there is a transaction where A is transferring some amount to B. So what A will do, A will fetch the current value, then A will do some arithmetic operation, and then after doing the arithmetic operation, A will update its value. So once A updates its value, this particular log is saved in the transaction log. So when we do write of A, it is not saved into the database, it is rather saved into the transaction log. And transaction log is deleted once we encounter the commit. So using this transaction log, we can recover our DBMS to a consistent state. So consider an example, if you are transferring 100 rupees to your friend and there is a sudden power outage or system crashes right after the transaction is committed. The changes, the transfer of 100 rupees will still be saved in the database. When the system is back up, both your account and your friend account will reflect the updated balance. So once the system is back up, it will show the updated amount to him as well as his friend. So this makes sure that even if there is any failure, everything is getting saved into our database and we have transaction logs to monitor each and everything at each and every point of transaction. So let's re-revise about ACID properties. So A stands for atomicity, which tells that either all operations should be executed or none of them should be executed. C stands for consistency, which says that if we are performing any read operation, the data should be up to date. If we are performing any write operation or update operation, we should be following the integrity constraints to update the value. Now third is isolation, which says that if there are two transactions, they should be isolated of each other. That is, first transaction should commit before the second transaction start. Now coming to durability, it says that if there are any committed changes in our database, that should be reflecting, that should be saved, even if there is any system crash or network failure which has happened. Now before starting with isolation level, let's just understand about isolation. So isolation says that if there are two transactions T1 and T2 which is running parallelly or concurrently, you can say, then these transactions should be isolated of each other. That is, if there are any operations which is happening in T1 should be isolated of operations which is happening in T2. Now this is what isolation is. Now what is this isolation level? So isolation level is the extent to which these operations are isolated of each other. Now whenever there is a read or write operation happening in T1, how much it is isolated with read and write operation happening in T2. So that is what isolation level is. It is the extent to which the isolation in the operations happens. Now why do we need to learn about isolation level? So in systems where multiple transactions are executed concurrently you can say parallelly, like there are threads on which the transactions are getting executed. So isolation levels manage the extent to which the operation of one transaction are isolated from those of other transaction. So the extent to which operation of one transaction are isolated to those of other transaction, that is isolation level. And we need isolation level because in systems there are sometimes multiple transaction which happens. So we need to know the extent to which, if there are multiple transaction happening, what is the extent to which their operations are isolated of each other. Now, isolation level help us to prevent common transactional anomalies. So there are some anomalies which happens while transaction, and isolation level help us to prevent them. Now, what are these anomalies? So the first anomaly is dirty read. Now, dirty read happens whenever we are reading uncommitted data from another transaction. So consider that there are two transactions T1 and T2, and as part of T1 I am writing some data in A, but as part of T2 I am reading some data of A. So as I have written some data into A, this particular data is updated in my internal memory. So if the value of A was 10, I have updated the A value to A plus 10. So now A value would be 20. And if I am reading A, then I'll be reading 20, not 10, because it is updated in the internal memory. It's not updated in the database yet because we haven't committed this transaction, but it's updated in the transaction logs, or you can say internal memory. And what if this transaction fails at some point? So if the transaction fails, we do a rollback and then A value would be updated back to 10. But here I have read the value of A to 20, so this becomes irrelevant. So that is why dirty read happens whenever we are reading any uncommitted data from another transaction. Now, what is this non-repeatable read? So non-repeatable read happens whenever data changes after it has been read within the same transaction. So consider that as part of T1, I am reading some data. As part of T2, I am updating that particular data. And as part of T1, again I am reading the same data. So here if the value of A was 10, if I updated the value of A to 20, here if I again read the value of A, it will come as 20. So during the read operation, I can see that first read operation gave me 10, but second read operation gave me 20. So the data changes happened, and after it has been read within the same transaction. So within the same transaction, if there are two read operations which are happening, and if in the next transaction there is any write operation which has happened, the values would be changed. Now coming to phantom read. So phantom read says that new rows are added or removed by another transaction after a query has been executed. Now consider that there is an employee table. In that particular employee table right now there are two records of employee E1 and E2. Now consider if I am doing a get query here. Right now I am getting two records, but consider if a new employee enters this particular organization. So I'll add that particular employee details as well in my table. Now again if I do a get on this particular table, it will give me 3 records. So you can see that the records has been changed. Again consider that if E2 decides to leave the organization, so we'll delete E2's entry from our DB or from our table. Then again if we do a get, then we will again get 2 records. So you can see that whenever there is some insertion or deletion happens, the get or the fetching of values or finding of values gives us different set of records. So new rows are added or removed by another transaction after a query is executed. It causes the phantom read. Whenever we are reading any uncommitted data, another transaction, dirty read happens. And whenever there is some data changes which happened in the same transaction, that is called as non-repeatable read. So these are some of the anomalies which are taken care as part of isolation levels. Now consider that if there are two transactions which is happening read as well as write operation, so there could be 4 possible combinations where if transaction 1 is executed and transaction 2 is executing, what are the operations they would be persisting. So the first one is transaction 1 can read value, transaction 2 at the same time can read value. Now coming to the next possible combination, transaction 1 can read value, transaction 2 can write the value as well. Now coming to the third combination where transaction 1 can write the value and transaction 1 would be reading the value. Coming to the fourth one where transaction 1 is also writing the value and transaction 2 is also writing the value. Since transaction 1 has read and write operations and transaction 2 also had read and write operations, we kept 1 as constant and then we switched between the different operations which were present here. Again we kept write as constant and then we switched between the different operations which is present here. So these set of operations can happen while two transaction is happening. So what is isolation level? It determines the degree to which the operations in one transaction are isolated from other transaction. So if there are two transactions T1 and T2 and if there are some set of operations which is happening between these two transactions, what is the extent to which these operations are isolated of each other? Now here we can see that there is a diagram on how a transaction happens. So consider that if there is an application, as part of application there could be multiple transactions. So there is two transactions, T1 and T2. Now T1 can also have some operations and T2 can also have some operations. So what we do whenever we perform any operation in any of the transaction, we go ahead and save it in our transaction logs. We don't go ahead and save it in the database directly, because if there are multiple transactions happening, there could be a possibility that there is some failure which is encountered and some of the transaction fails. Because of that, we don't go ahead and directly update in the DB. We go ahead and save it in the transaction logs, or you can say in the internal memory. And once the transaction is committed, we can say now it is ready to get saved in the database. We delete the transaction logs and we go ahead and save that particular into our DB. So this is how a transaction takes place. Now let's learn about anomalies in more depth. So the first anomaly is dirty read. So reading the data returned by a transaction that has not yet been committed. So let's understand from an example. Consider we are doing some changes into this A, and right now the value of A is 10. As transaction T1, we are updating the value of A to 20. Updating A to 20, and as part of T2, we are just reading the current value of A. So right now the value of A is 10. We updated the value of A to 20 as part of T1 as there is a write operation, and as part of T2 we are reading the value of A. Right now the A value from 10 it is updated to 20, so we will be reading 20. But consider that at some point this transaction fails. T1 fails. So whenever a transaction fails, there is a rollback which says that revert it back to its original state. So we have to revert back all the operation, and we have to again go ahead and revert the value of A which we updated to 20 to 10. Now the value of A is updated to 10, but as part of T2 we have read the value of A, and right now we know that the value of A is 20, but here the value of A is 10 as this particular transaction at some point failed. So you can see that this particular data or this particular read operation which we have performed is irrelevant, because now this particular data is irrelevant because in our database the value of A is 10. So whenever there is a transaction T2 which reads the data which is returned by transaction T1, and if T1 fails, it becomes irrelevant, because right now when we are doing a read operation from T2, it is reading the incorrect or data which is not present. So you can say a stale data. So it's reading a stale data and it is performing all its operation on the stale data. So whenever there is a write read happening, we call it as dirty read. Now let's learn about the next anomaly, that is non-repeatable read. So it says that reading the same row twice within the transaction and getting different values because another transaction modified the row and committed. Consider again we are doing some read-write operations on A. So as part of T2, what we are doing is we are updating the value of A again to 20. And as part of T1, we are reading the value of A and doing some operations. You can say reading the value plus doing some external operations that we are not sure right now. Doing operations. So what happened? As part of T1, we read the value of A, so that is 10. As part of T2, we read the value of A, again it is 10. We write the value of A, so now A is updated to 20, so it will be 20. And then we commit the changes, that is this 20 is now saved into our database. Until this point, it was saved into our transaction logs, or you can say internal memory, but whenever we encounter this commit, it is saved into our database. So right now the value of A is 20. So consider that because of some issue the T1 transaction stopped and it again began, and now again it is starting reading the value of A. Now here if it do a read of A, it will give me 20 as the 20 is updated in our database. But here if we read the value of A, it was 10, and on this 10 we were about to perform some operations, but right now we need to perform the operations on 20. So you can see that if there are multiple read which is happening in same transaction, and if another transaction commits some value or writes some value, then there is a non-repeatable read which happens. So consider if T2 modifies the data which T1 is already reading, and if T1 continues the transaction, the data will be changed. So here the data was 10 and here the data was 20. T1 stopped in between for some unknown reasons, and if T1 again started, it will read some changed data. So here the value was 10, but here the value has been updated to 20 because another transaction read the same data and committed on the same data. So whenever we are having some multiple reads in one transaction, and because of another transaction the multiple reads are giving different values, that is called as non-repeatable read. Now coming to the third anomaly, that is phantom read. So getting different set of rows in subsequent queries within the same transaction because another transaction inserted deleted rows and committed the data. So the same example, consider that there is an employee table. Right now we have 2 employees present in our table. First what I am doing, I am fetching the name of the employees. So right now I'll get only 2 values for the name of employees. Now consider that there is another transaction T2 as part of which we are inserting some data into our DB, or we are inserting new employee details E3 who has recently joined the company. So we have inserted the value of E3. Now names will be giving me 3 values. So again, if I fetch the name, it will give me 3 records, and here it was giving me 2 records. So you can see that here I was getting 2 records, but here I was getting 3 records because another transaction came and inserted a new set of data here. Again, there could be a deletion as well. Consider that if E2 left the organization. So as part of T2, I can go ahead and delete the entry of employee 2 as well. And again, if I fetch the names, I'll get the only 2 values. So you can see that there is some discrepancies in the records which we are getting while fetching because some other transaction came and inserted or deleted some of the records from our table. So this is the phantom read. Now we learnt about isolation level, we learnt about anomalies, but let's learn about types of isolation level. So there are 4 types of isolation level which help us with these anomalies. So the first one is read uncommitted, the second is read committed, the third is repeatable read, and the fourth is serializable. So let's learn about each and every one of them. So let's learn about the first isolation level, that is read uncommitted. So it is the lowest isolation level where transaction can see uncommitted changes made by another transactions. So if a transaction can see uncommitted changes made by another transaction, that is read uncommitted isolation level. So as you can see from the word also, it says that read uncommitted. So one transaction can read uncommitted changes. If a transaction T1 is writing a value to a table, T2 can go ahead and read that particular value before T1 commits. So if there are 2 transactions T1 and T2, if T1 is writing some value to a particular table, T2 can go ahead and read that particular value even if T1 is not committed. That is why it is called as lowest isolation level. So here you can see that there is a write read problem which is happening, because of which it doesn't takes care of dirty reads. The dirty reads is still there in this particular isolation level. Non-repeatable reads is also present here because again I can go ahead and read that particular value after some point in T2 and it will give me another data. Phantom read is also here because as part of this transaction we are not waiting for this transaction to commit, so we can go ahead and as part of T2 we can insert some data or delete some data from a particular table. Now coming to the next level, that is read committed. So it says read the value only when it is committed. So it ensures that any data is read during the transaction is committed at the moment it's read. So if there are 2 transactions T1 and T2, and if as part of T1 I am writing some value to A and as part of T2 I am reading some value of A, I can only perform this read operation whenever this particular transaction is committed and the data is saved into our database. So if T1 has done some write operation, T2 can only read the data when T1 has committed. So here you can see that after the commit I am reading the data, so there is no chances of T1 getting failed. So this read write problem is taken care here. So there is no dirty read which happens here. Now coming to non-repeatable reads. Non-repeatable reads can happen because consider here I am reading a data and again in this transaction T1 I am writing something and again I am reading the data. So here and here the data would be different. So non-repeatable reads can happen. Now coming to phantom reads. Phantom reads can also happen because what if transaction T2 comes and inserts some new record into the table. So that is why phantom read will always happen and non-repeatable read can also happen. Now coming to the third, that is repeatable read. So it ensures that if one transaction reads a row, it will see the same values for that particular row during the entire transaction. Even if other transaction modifies the data and commit, if transaction T1 reads the value, transaction T2 cannot go ahead and modify the value until T1 completes. So how this read and read problem was happening, consider as part of T1 and T2, T1 I was reading some value, as part of T2 I was writing some value, but because of some issues T1 stopped and after some time again it started. So if I read the value here and if I read the value here, they were different. But according to repeatable read, if a transaction reads a row, it will see the same value of row during the entire transaction, even if other transaction modifies the data and commits. So even if T2 commits the data or modifies the data, T1 will always read the same data which it read during the start of the transaction. So because of this, dirty read is stopped. Non-repeatable read will also not happen because it says that if there is any modification done as part of other transaction, that should wait until transaction T1 is complete. But it says that T2 can go ahead and insert some new rows. So because of this, phantom read is still existing here, but dirty reads and non-repeatable read is taken care. Now coming to the next transaction level, that is serializable. So it ensures that there is a serial transaction execution so that there is a complete isolation. So whenever there is a serial transaction execution, that is if there are two transactions T1 and T2, T2 should wait for T1 to complete. So if transaction T1 is executing, T2 must wait until T1 is complete. So if transaction T2 is waiting for T1 to get completed, it can't go ahead and insert any new row because T1 is still in progress. It can't go ahead and read some particular value or make modification to that particular value because again T1 is in progress, and it can't go ahead and read some particular value because again T1 is in progress. So there won't be any dirty reads because there is no read-write anomalies or write-read anomalies because T1 needs to be completed before T2 gets started. There is no non-repeatable read because again T2 has to wait for T1 to complete, and then only it can perform any read operation. Now coming to phantom read, that will also not happen because T2 can't go ahead and insert any new row until T1 is completed. So T1 should be completed for T2 to start. So there should be completion of T1 before T2. So that is why serializable has the most extent of isolation. Now what is a schedule? So schedule refers to the sequence in which a set of concurrent, or you can say multiple transactions, are executed. You can also say it as a sequence in which the operations such as read, write, commit and abort of multiple transactions are getting executed. So consider if there are two transactions T1 and T2. As part of D1 we are doing some read operation, as part of T2 we are doing some write operation. So the time order sequence in which these operations of multiple transactions are getting executed, that is what a schedule is. Now it is really helpful to ensure data consistency and integrity. Since it tells us that what is the sequence in which the operations are getting executed, it is very helpful in maintaining the data consistency and integrity of database. Consider if there are some transaction T1, T2 till Tn, then the possible number of schedule is n factorial. So if there are two transactions, the possible number of schedule is 2 factorial. Now here if you can see, there is a schedule SC1 where we have two transactions T1 and T2. We have mentioned all the operations which are happening in these two transactions, including the read as well as write operation. Now here you can see that we are getting a time order sequence, like first T1 started its read operation, then there was a context switch, then T2 started its execution, then again there was a context switch, then T1 committed the data, then again there was a context switch and T2 committed the data. So we can know the time order sequence or the sequence in which the multiple operations of different transactions are getting executed. Now here you can see that in the schedule we can see the commits. So if commits are present in the schedule, we call it as a complete schedule. If commit statement is not present in the schedule, that is changes are not saved into the database, we call it as incomplete schedule. So let's see in more depth. So incomplete schedule is a schedule where not all transactions have reached their final state of either commit or abort. So final state in any transaction is either commit or you can say rollback. So if the transaction succeed, we commit all the changes into the database. If transaction does not succeed or face any network failure or system failure, we roll back all the changes. So whenever some of the transaction in a schedule does not reach its final state, we'll call it as incomplete schedule, and when they reach, we call it as complete schedule. So here you can see that there are two transactions T1 and T2. T1 performed some read as well as write operation, then there was a context switch, then T2 performed some read as well as write operation, then there was a commit which was done for T2, but there was no commit which was performed for T1. So we can say that this is an incomplete schedule because T1 hasn't reached to its final state and is still in progress. So whenever any part of transaction which is a part of schedule which hasn't reached to its final state, we call it as incomplete schedule. Now coming to complete schedule, so a complete schedule is one where all transactions in the schedule have either committed or aborted, basically have reached their final state. So here if you see, there are two transactions T1 and T2. T1 started its execution and reached its final state, so T1 is already in its final state. Coming to T2, T2 started its execution and reached its final state. So here both of the transactions T1 and T2 are in final state, so we can call it as a complete schedule. So basically if the transaction in a schedule has reached its final state, we call call it as complete schedule. If they haven't reached its final state, we call it as incomplete schedule. Now coming to the types of schedule. So the first one is serial schedule, the second one is concurrent or non-serial schedule, third is conflict serializable, fourth is view serializable, fifth is recoverable, sixth is irrecoverable, seventh is cascadeless, eighth is cascading, and ninth is strict schedule. So let's learn about each and every schedule in depth. So coming to the serial schedule. So a serial schedule is one where transactions are executed one after another. We can say it like if there are two transactions, T1 and T2, then T1 should commit to completion before T2 starts. So according to serial schedule, if there are two transactions T1 and T2, so T2 should only start when all the operations of T1 are committed or either saved in database, or we can also say have reached their final state. So once they have reached their final state, only then T2 can start, else T2 can't start. So if you see the schedule here, there are two transactions T1 and T2. T1 started its execution, read A, write A, and then there is a commit. So T1 has reached to its final state. Now only T2 can start, before this T2 can't start. So there is a serial execution. First T1 will complete all its operation, then T2 will start its operation and complete it. Then T2 started, and here T2 also completed. So you can say that T2 starts only after T1 is completed, committed, or reached its final state. Now here you can see that there is a serial execution which happens, like first transaction T1 will be completing, then only T2 will be starting. That is why it is known as serial schedule, because it has serial execution of transactions. So let's see the advantages and challenges which is faced in the serial schedule. So coming to the first advantages, it follows the ACID properties, that is transactions are isolated from each other. So in the serial schedule, what happens is, if there are two transactions T1 and T2, T1 needs to perform all its execution, only then T2 can start. So we can say that these particular transactions are isolated of each other. Any operation of T2 can't go ahead and hamper any operation which is getting performed in T1. So there is a level of isolation which is maintained between T1 and T2, because T1's all execution are done, only then T2 starts. Now the second point is it maintains consistency. So consistency is obviously maintained here because T1 is committing all the changes into the database once it's succeeding. So even if we start T2 and even if we perform some operation on the same data item, all the data has been updated into the database. So there is no data inconsistency which would happen, because there won't be any read write, write write, write read conflicts which would be occurring. So we won't be going ahead and updating any invalid data in our database. T1 has committed all the changes, T1 has successfully updated it in the database, and then only we are performing operations of T2. So let's see the challenges. First challenge is, since there is a poor throughput, that is number of transactions completed per unit time, and the memory utilization is also poor, that is why it is not suggested, as it can be inefficient. So consider in the serial schedule, if there are two transactions T1 and T2, T2 needs to wait for T1 to get completed, but consider T1 take 5 minutes to get completed. So T2 can only start after 5 minutes. So if you see the throughput, that is number of transactions completed per unit time, is very less. That is why there is a poor throughput. And memory utilization is also poor, because if T1 is executing all its operation, T2 is sitting idle, and CPU core is only able to succeed all the T1 operations, not the T2 one. So T2 is sitting idle, and CPU cores are also not getting utilized to its max. So we can say the memory utilization is also poor. The second is, since wait time is high, less number of transactions are completed. Now T2 needs to wait for T1 to complete, and T1 is taking 5 minutes. So the wait time is very high. In 5 minutes, in a real life scenario, there should be 1000 or more than 1000 transactions which should be done. But here, in that particular time, only one transaction is getting completed. Because of all these reasons, it is suggested not to use the serial schedule, even if it has a higher consistency, but the throughput is very low, the number of transactions getting completed per unit time is low, memory utilization is low, or you can also say the wait time is very high. So because of all those things, serial schedule is not suggested. Now coming to the second schedule, that is a non-serial, or you can say concurrent schedule. Now from the name it's clear, non-serial, so there is no serial execution. So a non-serial schedule is one where multiple transactions can execute simultaneously. Operations of multiple transactions are alternate or interleaved. So what is this alternate or interleaved? So here if you can see, there are three transactions T1, T2 and T3. Here T1 started its execution, then there was a context switch. T2 started its execution, then again there was a context switch, and then T3 started its execution. So all these transactions are starting their execution simultaneously. So these are interleaved, or you can say alternate execution. We can say it like if there are two transactions T1 and T2, T2 doesn't need to wait for T1 to commit, it can start at any point. So if you see from example, T2 or either T3 can start their execution, they don't need to wait for T1 to get completed. That is what a concurrent schedule is. So here T2 didn't waited for T1 to commit. Now here you can see that at later point T1 is committing its changes, but T2 and T3 have started their execution. So the wait time is very low. Now coming to the advantages and challenges, first is better resource utilization, because at the same CPU core T1 is also starting their execution, T2 is also starting, T3 is also starting. So resource is getting utilized at its max. Second is wait time is not involved, because T2 doesn't need to wait for T1 to get completed. One transaction doesn't need to wait for running one to finish. So the next is throughput is very high, that is the number of transactions getting completed per unit time, because T1, T2, T3 all are starting at some instant of time and they are not waiting for other one to complete. So it is starting at this particular point, it is starting at this time, it is starting at this time. So at some time T double dash, we will be able to get all these transactions getting completed. So the number of transactions getting completed per unit time would be more. Now coming to the challenges. So first is consistency issue may arise because of non-serial execution. It requires robust concurrency control mechanism to ensure data consistency and integrity. Now in non-serial execution, what happens if there are three transactions T1, T2 and T3? As part of T1 we are reading some data item, as part of T2 we are writing some data item, as part of T3 we are reading some data item. So we have read the data item A, then we have written or updated some value of data item A, then again we have read the value of A. But consider at some point this T2 fails. So this particular transaction T3 has read the value which was there in T2 or which was updated from T2, right? But this particular transaction failed, so there won't be any update happen. But as of now the T3 has read the value which was updated here. So this particular value becomes invalid and there is data inconsistency which happens. So that is why there are some concurrency control mechanism which make sure that these particular things doesn't happen, and serializability concept is also there for this. So we can use serializability and concurrency control mechanism to ensure consistency so that none of the invalid data is updated or there is no inconsistent data which is present in our database. So coming to the third schedule, that is conflict serializable schedule. So a schedule is conflict serializable if it can be transformed into a serial schedule by swapping adjacent non-conflicting operation. Now what are these conflicting and non-conflicting operation? So consider if there are two transactions T1 and T2, we can perform some operations on them. Consider there is a read operation on T1, read operation on T2. Read operation on T1, write operation on T2, write operation on T1, read on T2, and write in T1 and write in T2. So here if you see, if we perform read operation on T1 and T2 both, so they are reading the same data item although, but they are reading the same value, right? They are not updating anything, they are reading the same value, so there is no issues here. But coming to here, if any transaction we are reading some value and at part of next transaction we are updating that particular value, so there will be a read-write conflict. Coming to this, so if at part of one transaction we are writing some value or updating some value, and as part of another transaction we are reading that particular value, so there will be a conflict. Coming to the same write, if we are writing some value as part of one transaction and then again writing some value of part of another transaction, so there will be a conflict, because there could be a possibility that we are reading some value and here we are updating some value, but at some particular point this particular transaction fails. So if we are reading the value again, we will be reading inconsistent value. So these all operation can cause inconsistency. You can say that whenever there is a write operation involved, it can cause inconsistency. So we call these pairs as conflicting pairs. Because of these, there could be some conflicts which can arise, or there could be inconsistency in data which can arise. And this pair is non-conflicting because even if we are performing read operations as part of multiple transactions, there is no issues. So here you can see the conflict pair is read-write, write-read, write-write when performed on the same data item. But there could be a possibility that as part of T1 I am reading the value of A, but as part of T2 I am writing the value of B. So here the data items are different. So these are also a non-conflicting operation. So if we go to the non-conflicting pair, read when performed on the same data item, read when performed on the different data item, write when performed on the different data item. Since we are performing on different data items, so there would be no consistency issue, because we are not going ahead and updating the value of B, we are going ahead and updating the value of A, and we are reading the value of B, so there won't be any issues. So let's come back to the conflict serializable schedule. So as part of conflict serializable schedule, what we do is we take the concurrent schedule, we change its execution from non-serial to serial, so that the consistency issue which was coming in non-serial execution, or you can say in the concurrent schedule, is encountered or taken care. So what we do here is we find a conflict equivalent. How we can find a conflict equivalent? By swapping the adjacent non-conflict pairs, and in that conflict equivalent we see that if by swapping we are able to achieve a schedule where there is no conflicts. So coming to this schedule, if we see the non-conflicting adjacent pair, so T1 has read of A, T2 has read of A. So this is a non-conflicting pair because we are performing only read operation on the same data item. Coming to T2 and T1, again read of A, write of A, this is conflicting. Coming to here, write of A, again conflicting, and then write of B. So here we can see that there is only one non-conflicting pair. So what we have to do is we have to swap these non-conflicting pairs, and then we can get the conflict equivalent, and then we can see that if that conflict equivalent has any conflicts or not. For now, we won't be looking much more depth into this particular schedule because we have a dedicated lecture on conflict serializable schedule. So here you can see that RA of T1 and RA of T2 is non-conflicting, RA of T1 and WA of T2 is conflicting, having read-write conflict, and WA of T1 and WA of T2 is conflicting because they have write-write conflict. So the fourth schedule is view-serializable schedule. Now it is also part of serializability. So serializability is a method which is used so that we can encounter the inconsistency issue which was coming in the concurrent schedule. As part of serializability, we do a conflict serializability and a view serializability. So we would be learning about all these in next set of lectures. So view serializability ensures that the database state seen by the transaction in a concurrent schedule can be replicated by some serial execution of those transactions. So in view serializable schedule, or you can say view serializability, we are making sure that if there is a concurrent schedule, they have a serial execution so that the consistency issue is encountered. Now, whenever we find a cycle in our conflict graph, we don't know if our schedule is serializable or not, so we use the view serializability here. So serializability is used to encounter the inconsistency issue which was coming in our concurrent schedule. Now, as part of serializability, there is conflict and view serializability. In conflict serializability, we draw a conflict graph. Now, if this particular graph has any cycle, we go to the view serializability to check if this schedule is a serializable schedule or not. If there is no cycle, we can say that this is a serializable schedule. If there is a cycle, we go to the view serializability and check for some conditions for a view equivalent. If all these conditions are met, we say that this particular schedule is a serializable schedule. If not, we say that this particular schedule is not serializable. Now, all these things may be sounding confusing to you, but don't worry, we would be talking about each and everything in depth in next set of lectures. For now, you can only think that view serializable schedule is a schedule which is view serializable. So a schedule is view serializable if its view equivalent is equal to a serial schedule execution. So whenever a schedule is view serializable, its view equivalent is equal to a serial schedule or serial execution. So whenever there is a serial execution of a view equivalent which we have found out for a schedule, we call it as a view serializable schedule. So coming to the next schedule, that is recoverable schedule. So a recoverable schedule ensures that if transaction reads data from another transaction, it should not commit until the transaction from which it read has committed. So consider if there are two transactions T1 and T2, and T2 is reading some data which is updated by T1. So T2 shouldn't commit until the time T1 commits. So T2 should always wait for T1 to commit, only then T2 should commit. If it commits before, and what if at some point this transaction fails, this particular operation will read some invalid data, because as T1 failed, there was a rollback and this particular operation is nullified now. So this data is invalid. So we have to wait for the transaction from which we are reading the data to be committed so that we commit the correct, or you can say the consistent data. So this helps in maintaining the integrity of database in case a transaction fails. So if at any point T1 fails, we will be able to recover T2 because T2 hasn't committed all the changes into the database. It's present only in the transaction logs. Now coming to the sixth, that is irrecoverable schedule. An irrecoverable schedule allows a transaction to commit even if it has read a data from another uncommitted transaction. So if the transaction is uncommitted, it allows another transaction to commit the data. This can lead to inconsistency and make it impossible to recover from certain failures. So what if transaction T1 fails at some point and we have committed the data based on what we have read from the updated value of T1, which is not updated into the database because the transaction has failed. So this will have a invalid data, and that particular invalid data would be committed or changed into the database. So it will cause inconsistency in the database because we are updating some invalid value or the value which is not consistent into our database. So the next schedule is cascading schedule. This schedule happens when the failure or abort of one of the transaction causes a series of other transactions to also abort. So consider if there are three transactions T1, T2 and T3. T1 has started its execution, T2 also started and T3 also started. At some point T1 failed. So here you can see that there was a write of A which was present in T1 and T2 read the same data which was updated as part of T1, but T1 failed. So this also needs to abort and this also needs to abort because we won't be updating any inconsistent value or we won't be reading any inconsistent value which is not updated in our database. So there are multiple aborts which are happening. So here you can see T1 writes to A, so T1 writes a data item to A. T2 reads it, so T2 reads the uncommitted value of A which is written by T1. Now if T1 fails and aborts, T2 must also abort because it has read an uncommitted value which is from T1, and this particular value is also read by T3, so T3 also must abort. Now there are some issues. First is the performance degradation because multiple transaction needs to be rolled back. So there were some transaction which started, but because of one transaction failure, there are multiple rollbacks which is happening. So there is a performance issue. Second, improper CPU resource utilization because we use the CPU resources to perform these three transactions, but because of the failure of one transaction, all the transactions have to fail because they have read some uncommitted changes of that particular transaction. Now coming to the next schedule, that is cascadeless schedule. So it ensures transaction only read committed data such that the abort of one transaction does not lead to the abort of other transaction that have already read its uncommitted changes. So it makes sure that if any transaction is reading any value, it should always read a committed value. It shouldn't read a value which is not committed. When a transaction has already committed all its changes to the database, and if we are reading the committed changes, there is no issues which will occur here because these are all the changes which are saved into our database and there is no chance of failure which occurs after commit because this is the final state. So this particular read operation won't have any inconsistent data. So T1 writes to A, T1 has written some value to A, and T2 reads from A. So T2 reads the committed value of A because it has been saved into the database, ensuring that there is no write read problem which is happening. So in the cascading schedule there was a write read problem which was happening, but here it is not happening, and T2 does not read any uncommitted data because this data is committed. So there is no cascading aborts in this particular schedule. But here it says that one should only read committed data. But what about the write operation? So they haven't told anything about the write operation. They have only told about the read operation, that one should always read the committed data. But what if there is a write problem which can come, right? So there are some issues. First is the write problem is encountered because it has only told that it can read committed data, but not anything related to write operation. Second is performance overhead is there because again this needs to be committed. So this particular transaction can only read after it is committed. So it needs to wait for this to get committed. Coming to the last schedule, that is strict schedule. So it ensures that transaction is not allowed to read as well as write a data item that another transaction has written until the first transaction has either committed or aborted. So it makes sure that there is no read or write operation performed until that particular transaction from where we are reading or writing the data has been committed or aborted, basically has reached its final state. So it prevents the cascading aborts. So what will happen in T1 and T2? So T1 needs to complete all its operation, only then there could be any read as well as write operation which would be performed. So the write issue which was coming there, or write conflict which was coming there, is resolved now, because it can only write a data or it can only read a data once the transaction is committed. So T2 cannot read or write the value of A until T1 has committed. This ensures that T2 only sees the committed value of A. So this is how strict schedule prevents the cascading aborts and make the consistency at its peak. So I was getting so many queries on concurrent and parallel schedule. People were thinking that concurrent and parallel schedule are the same, but there are some differences between concurrent and parallel schedule. So let's learn about them. So first let's go through the definition. So concurrent scheduling manages multiple tasks at the same time. Tasks can overlap in their execution period but do not run exactly simultaneously. Consider if there are three transactions T1, T2 and T3. Now T1 can start at any instant T, T2 can start at any instant T dash, and T3 can start at any instant T double dash. So here you can see that all of these transactions, their execution may overlap, or you can say at the same time not all these three transactions are starting. But coming to parallel scheduling run multiple tasks simultaneously using multiple cores or processor. So in parallel schedule there are multiple cores, or you can say processor, which helps the transaction to run parallelly at the same instant of time. So all these three starts at instant of time T. So each task is executed on a separate core or processor at the same time. So all the three tasks are executed at the same time, while in concurrent schedule they can start at any instant of time. Now coming to the execution. So it is achieved on a single core processor through context switching, where the CPU rapidly alternates between the tasks, creating the illusion of simultaneous execution. So what happens when T1 starts and when T2 starts at any instant T dash, there is a context switching which happens between T1 and T2. Then again for T2 and T3 there is a context switching which which makes it as alternate, or you can say concurrent execution. But coming to parallel, it requires a multi-core processor or multiple processor, which each core handling a different task concurrently. So all these three cores will be handling different tasks, but they would be handling it concurrently. So all these three cores will run at the same time. They are running on the different cores, all the transactions, and each core will handle different set of tasks. Now coming to example. So consider an example where multi-threading on a single CPU core, where thread takes turns in the CPU. Now there are three threads, T1, T2 and T3. What will happen? They will not run on different processor or cores. They will only use this single CPU core. So first T1 will go and start its execution. Then there will be a context switch. Then T2 will go and start its execution. Then there will be a context switch. Then T3 will go and start its execution. So again there is a context switch which is happening between the threads, or you can say between the transaction, because they are utilizing the same CPU core. But coming to the parallel, multi-threading on a multi-core CPU, where threads can run concurrently on different cores. So consider if there are three cores and there are three threads. These three threads can run concurrently on different cores. So T1 can run on this particular C1, can run on C2 core, and T3 can run on C3 core. So they don't need to wait for their turns. They have the CPU core and they can go ahead and execute their thread there only. So this is the basic difference between concurrent and parallel schedule. So if someone asks you if concurrent and parallel schedule are the same, it's not the same. There are some differences between the concurrent as well as parallel schedule. Now, if you remember, in the schedule lecture, we learned about serial as well as concurrent schedule. Now, what are these? So, in serial schedule, all the transactions have a serial execution. In concurrent schedule, all the transactions have interleaved, or you can say alternate execution. Now, there were some advantages as well as disadvantages for serial as well as concurrent schedule. Now, coming to serial schedule, the advantage was it follows the ACID properties, so the consistency was maintained here. The disadvantages was there was very low throughput, like the number of transactions completing per unit time were very low. The wait time was very high, and coming to resource utilization, that was also very low. Now in concurrent schedule, the advantages was the throughput was very high, like number of transaction completing per unit time. The wait time was very low. The resource utilization was very high, but the consistency was low, or the consistency wasn't maintained. So because of multiple advantages, we use concurrent schedule everywhere. But there was one disadvantage, that was consistency. So it was not following the ACID properties. Because of this consistency, we introduced serializability and some concurrency control mechanism, which makes sure that even if the schedule is concurrent, it follows a serial execution. So serializability ensures that the concurrent transaction yield results that are consistent with some serial execution, that is the final state of the database after executing a set of transactions concurrently should be the same if the transaction had been executed one after another in some order. So serializability makes sure that if there is any concurrent schedule and if we are serializing that particular schedule, so S dash would be having a serial execution. So even if S dash is formed from a concurrent schedule, we make sure that S dash follows a serial execution so that the consistency is maintained. Now in case of concurrent schedule, consistency issue may arise because of non-serial execution, because of which we use the serializability concept. Now coming to serial schedule, we don't need to use serializability because the execution is already serial. Now in serializability, there are two types of serializability. First is conflict serializability and second is view serializability. So how do we know that this particular concurrent schedule is serializable or not? So first we need to check for conflict serializability followed by view. So in conflict serializability, we check that if there is any cycle which is detected in a conflict graph. If a cycle is detected, we go to the view serializability and we check that if the view equivalent follows some condition. If it is followed, we say it is serializable. If it is not followed, we say it's not serializable. If the cycle is detected, we go to the view serializability. If the cycle is not detected, we say that this particular schedule is serializable. So we first need to check for conflict serializability. If no cycle is formed, we can say that that particular schedule is a serializable schedule or that particular schedule is a conflict serializable schedule. If the cycle is detected, we need to check for view serializability, and if in the view serializability also some conflicts arises or if the condition is not met, we can say that that particular schedule can never be serializable or can never have a serial execution. Now how do we form the conflict graph? So conflict graph is basically formed on the basis of nodes as well as edges. So how we form the graph? In the conflict graph, the nodes is represented as the transactions in the schedule and edges is represented as conflicts in the schedule, and we need to detect if the graph has a cycle or not. Now in a serial schedule, we don't need to form the conflict graph because there are no conflicts. If you see here, all the execution of transaction 1 is getting completed, only then transaction 2 is starting. So there will be no edges because edges represent the conflicts. But here if you see, there are no conflicts. So we can say that there won't be any conflict graph for a serial schedule. Now coming to the concurrent schedule. So here there are two transactions T1 and T2. So we need to represent it using the node. So it is T1 and T2. Now coming to the execution. So here if you see, it starts with T1, then there is a context switch, then there are some execution in T2, then again there is a context switch, and then again there is a execution in T1. So if we need to draw the conflict graph for this, we can see that there are two edges and there is a cycle which is detected in this particular graph. So T1 goes to T2 and then again T2 goes to T1. So there is a loop, or you can say cycle, which is detected in this particular graph. So a concurrent schedule does not always have a cycle. So it's not always possible that a concurrent schedule will be having a cycle. It can have a cycle, it can't have a cycle. If it has got a cycle, we need to see for the view serializability. If it doesn't have a cycle, we can say that it is conflict serializable, because of which it is serializable. So a concurrent schedule can be conflict serializable, meaning that it is equivalent to some serial schedule of transaction and its conflict graph does not have any cycles. So if there are no cycles, we can say it is conflict serializable, that is it is serializable. If there is any graph, we need to check for the view serializability. Now since a cycle is detected, we need to serialize them. So we use the serializability here. First we use the conflict serializability to detect the cycle using the conflict graph, and then we use the view serializability to check if the schedule is serializable after a cycle has been detected. So in this way we use the serializability concept. Now why do we need to serialize them? So to avoid the consistency issue which may arise because of non-serial execution. So in the non-serial execution, we can have some consistency issue and we don't want our transaction to be inconsistent, because of which we use the serializability concept. Apart from serializability, we also use some concurrency control mechanism, of which we will be talking in the next set of lectures. So coming to the types of serializability, there are two types of serializability, conflict and view. In conflict serializability, we check that if the conflict graph has any cycle or not. In view serializability, we check that if a view equivalent is following some conditions or not. We'll be learning about all these as well in the next set of lectures. So before starting, let's just re-revise some older concept. So what was serializability? Serializability is a property of a schedule where the outcome is equivalent to some serial execution of transaction. So why do we need serializability? So in concurrent schedule, there was a non-serial execution of transaction, because of which there was some consistency issues which were coming into our database. So to encounter this consistency issue, we had serializability as well as some concurrency control mechanism. Now, as part of serializability, we make sure that if there is a schedule which has concurrent executions, or you can say interleaved execution, we'll try to have a serial execution of that particular schedule so that we can use the concurrent schedule and can also encounter the consistency issues. Now, what is conflict serializability? A schedule is said to be conflict serializable when one of its conflict equivalent is serializable. So basically, if a schedule can be transformed into a serial schedule by swapping non-conflicting operations, then the schedule is conflict serializable. So when do we say a schedule is conflict serializable? So ideally there are two methods which we can use. First is, what we can do is we can swap the non-conflicting operations, that is the adjacent operations, and we can find a conflict equivalent schedule. Now for this conflict equivalent schedule, if there are no conflicting operations present after swapping all the non-conflicting operations, we can say it is conflict serializable. Second is using the precedence, or you can say the conflict graph. So in the conflict graph, we see that if the conflict graph has any cycle or not. If it has cycle, we can say it is not conflict serializable. If it doesn't have cycle, we can say it is conflict serializable. So let's learn about first the conflict equivalent, and then we will go to the precedence graph. So conflict equivalent. If a schedule S1 is formed after swapping adjacent non-conflicting operations or pair in a given schedule S, then S1 and S are conflict equivalent. So if there are two schedule S and S1 is formed after swapping the non-conflicting operation of S, then we can say that these particular schedules are conflict serializable. Now what are the conflict and non-conflict pairs? So conflict pair are read-write, write-read, write-write when performed on the same data item. What are non-conflict pair? So they are read-read when performed on the same data item, read-read when performed on the different data item, write-write when performed on the different data item. So let's see. So why these are non-conflict pair? Consider if I am reading a data item A, and then as part of another transaction I am reading the data item B. So there is no conflict, right? Because we are only reading the value, we are not reading any modified value, or we are not updating any value, we are only reading the value. So it will not cause any consistency issue, because of which it is called as non-conflicting. Coming to here, so we are again reading the same data item, but again it won't cause any conflict or consistency issue. Coming to here, so we are writing a data item A and we are writing a data item B. So we are writing into different data items as part of transaction T1 and T2. So these are also non-conflicting, because if I am writing to data item A and again I am reading to that particular data item only, this could be conflicting, but these are not conflicting. Now coming to this one, where in transaction T1 we are reading the data and in transaction T2 we are writing the data, but the data items are different. Here we are reading from A and here we are writing in B. So again, if the data item are different, there is no conflict. If the data item is same, if only there is a write operation involved, there would be a conflict, else there would be no conflict. Now coming to the conflict pair, we are reading a data item A and then we are writing some value to that particular data item A. So there is a read-write conflict. Again, we are writing to data item A and then we are reading it. Consider after some time this particular transaction fails. So we are reading some invalid data, because if it fails, it will abort and roll back and it will come back to its original value. But here we have read the updated value. So it will have a invalid value. That is why it is a conflict pair. Now coming to write-write, where we are writing on the data item, again we are writing on the data item as part of transaction T2. So these all pairs are the conflict pairs, where we are performing any write operation in any of the transaction on the same data item. These are the non-conflict pair, because if we are performing these operations, there is no inconsistency issue which is encountered in our database. So how to achieve a conflict equivalent schedule? So when a schedule can be transformed into a serial schedule by swapping adjacent non non-conflicting operations. Conflict arises when two transactions assess the same data item and at least one of them is a write operation. So whenever one of them is a write operation, and if there is any operation which is getting performed on the same data, write operation, read operation, then we can say that there is a conflict which is arising. Now, why we are only swapping the non-conflict pairs and not the conflict ones? So if we swap the conflict pairs, the order of execution, if it was read of A, write of A, the result of values may change, as first we were reading A and then writing or modifying A, but now it will be writing into A and then reading the modified value. So consider this was before changing the conflicting operation, and this is after changing the conflicting operation. So it would be T1 of WA and T2 of RA. So here if the value of A was 10, it reads the value of A, so it would be 10. It's write the value of A, that would be consider A plus 10. So it is 20. Now here it is writing the value of A. So A would be A plus 10. So that is 20. And now it is reading the value of A, that is 20. So if you see that here the value of A while reading was 10, but here the value of A while reading is 20. So if we switch the conflicting pairs, there could be a chances of data inconsistency, because the result which we were getting earlier and the result which we are getting after is different. So the modified value result might change if we change the order of execution. So let's solve a question where we have to find the conflict equivalent for a given schedule S1. So this is the schedule. What we have to do is we have to find the non-conflicting pairs and we have to swap it. Then we have to see that again if there are any non-conflicting pairs, and then again we have to swap it until the time we don't get any non-conflicting pairs. So let's see. So here the read is happening on X. Here the write is happening on X and read is happening on X. So there is a same data item, so there is a write-read conflict. Coming to here, so there is a read in X and there is a read in Y. So these is non-conflicting operations. So we will just mark it like this, that these both are non-conflicting operation. Coming to here, so there is read in Y and then there is a write in Y. Coming to here, there is a write in Y and then there is a read in Y. So there is a read-write conflict. So first is find the adjacent non-conflicting pairs and do a swap. So we have found the adjacent non-conflicting pairs, so we have to swap them. So Rx will come here and Ry will come here. So after the swapping, we have got Rx, Wx, Ry, then Rx has come here, then Wy and Ry. Now again we need to see that if there are any non-conflicting pairs. So this is Rx, then there is Wx, then there is Ry and then there is Rx. So this is again a non-conflicting pair. Now coming Rx, Wy, so this is also a non-conflicting pair. And coming here, so there is Ry. So for this pair we have already swapped, but here we haven't swapped. So we have to swap Rx here and Wy here. Since we are reading the X and we are writing on Y, so the data item are different, that is why it is a non-conflicting operation. So after swapping this, the schedule we get is Rx, Wx, Ry, and this is being swapped to here and this is being swapped to here. So it will be Wy, then here it will be Rx and Ry. Now let's see the schedule again. So it's Rx, Wx, Ry, Wy, Rx, Ry. So here you can see that write is happening on the Y data item and read is happening on the X data item. So there are no more conflicts which is left in this particular schedule. But what if there is a schedule and I found the view equivalent of that particular schedule, but there are still some conflicting pairs which is present in that schedule. So that particular schedule can't be a conflict equivalent schedule for a given schedule S1. And we can also say that it's not conflict serializable. Now this particular method we don't use very often, because if the schedule is very large, then there would be a lot of complexities. That is why we use the precedence graph method or the conflict graph method. Now how to check whether a schedule is conflict serializable or not? So conflict occurs when two operations from different transactions assess the same data item and at least one of them is a write operation. So we use the conflict graph and precedence graph here. So conflict graph or a precedence graph is a directed graph which is used to determine the conflict serializability. The nodes represent the transaction, the edges represent the conflicts between the transaction. So we will be drawing a conflict graph where the nodes will be representing the transaction, there will be a directed graph, and the edges would be representing the conflicts between those transactions. So let's see how we can draw the conflict graph. So conflict graph has node, edges and cycle. Now node, each transaction in the schedule is represented as node in graph. So if there are two transactions T1 and T2, we represent T1 and T2 as the node in the graph. Now coming to edges, an edge from transaction Tx to Ty denoted Tx, Ty is added if an operation of Tx conflicts with any operation of Ty. So if in Tx, or you can say T1, if there is any operation, consider read of A, which conflicts with some operation which is present in T2, then we represent the edges, or we can say we represent the conflicts. So Tx operation precedes Ty operation in the schedule. So Tx operation will always precede the Ty operation in the schedule. Now coming to the cycle detection. So schedule is conflict serializable if and only if the conflict graph is acyclic. That is, there is no cycle in the graph. If there are no cycles in the graph, it means that the schedule can be serialized without violating the order of conflicting operations. So if there are no cycles in the graph, we can say that that particular schedule is conflict serializable. That means that that particular schedule is serializable. But if there is any cycle, we have to go to the view-serializability, which is another type of serializability. So let's see that how, using the conflict graph or precedence graph, we can tell that if a particular schedule is conflict serializable or not. So check if the given schedule is conflict serializable or not. So there are three transactions T1, T2 and T3, and there are some operations which is getting performed on data item A as well as data item B. So there are two data items and there are three transactions. So let's see. So the step one is we have to find the conflicts in the schedule. How we can find the conflict is, first, if we are seeing for any transaction T1, we have to look in T2 and T3 for any conflicts. If we are checking in T2, we have to look for T1 and T3 for any conflicts. And if we are looking for T3, we have to check for T2 and T1. Now what are the conflicts? So there could be a read-write conflict performed on the same data item. There could be a write-write conflict performed on the same data item. There could be a write-read conflict performed on the same data item. So if we are checking for any write operation in a given transaction, we have to check for write as well as read. And if we are checking for any read operation, we have to only check for write operation. So let's see. So the first operation is read of A. So we have to check that if in T2 or T3 there is any write of A. So let's see, in T3 there is. So there will be a read-write conflict where there would be a conflict between T1 and T3 on A. Now coming to the next operation, that is read on A. So let's see if there is any write of A. Yeah, it is present in T1. So there will be a read-write conflict of T2, T1 on A. And let's see in T3, yes, there is present. So there will be a read-write conflict on T2 and T3 on A. Now let's come to this data item, that is write of A. So let's see, is there any read of A as well as write of A? So is there any read of A present? No. Is there any write of A present? Yes, it's present. So we can say that there will be a WW conflict between T1 and T3. We are not checking for the older operations because them we have already discarded or we have already found out the conflicts. So we are only looking for the operation for which we haven't found out any conflicts. So there will be a write-write conflict which would be present between T1 and T3 on data item A. Now coming to this one, write of A. Is there any read of A or write of A present? No, it's not present. Now coming here, write of B. Is there any read of B or write of B present? Yes, it's present. So it would be T2 to T3, write-read conflict on B. Now coming here, read of B, there won't be any conflicts. So these are all the conflicts which we have found out in the schedule. Now the step 2 is we have to find the nodes. So the nodes are all the transaction T1, T2 and T3. So we have found out the nodes. Step 3 is we have to find the edges and the conflicts. So conflicts we have already figured out. Now we have to find the edges. So there is a read-write conflict which is happening on T1 and T3 on the data item A. So on T1 we are performing a read of A and on T3 we are performing a write of A. So here the value of A is getting updated, but there is a read which is getting performed before even updating the value. So there will be an edge from T1 to T3 because T1 reads A before T3 writes A. Now there would be an edge from T2 to T3 because of read-write conflict. There will be an edge from T1 to T3 because of write-write conflict, T2 to T3 because of read-write conflict, and T2 to T1 because of read-write conflict. So here you can see that some of the edges are getting repeated, T2, T3, T2, T3. So we don't need to write for the repeated edges. So we can just discard one and we can only use one of the edge. And here also there is T1, T3 which is getting repeated twice. So we can only use one edge because we have already identified that there is a conflict. So there will be only 3 edges, T1 to T3, T2 to T3 and T2 to T1. So now we have to draw the graph. So first we'll draw all the nodes. So that is T1, T2 and T3. Now we have to form the edges. So there is an edge from T2 to T1. So this is the edge. There is an edge from T1 to T3. So this is the edge. And there is an edge from T2 to T3. This is the edge. So these are all the edges. But can you see that if there is any cycle formed or not? So there is no cycle formed. So since the graph has no cycles, we can say that this particular graph is conflict serializable. So in the step 5, we say the same. If the graph has cycle, it is not conflict serializable or serializable. If not, let's find the serial execution of transaction. So since it has no cycle, it is conflict serializable, means it is serializable. So if a graph is serializable, or if we can say a schedule is serializable, then we can find the serial execution, that how the serial execution will happen or which particular transaction will start first and followed by others. So let's see. So let's find the serial execution of transaction. So we have to find the possible combination first. So there are 3 transactions. I told that the number of possible schedule when there are 3 transactions is 3 factorial, or whenever there is n transaction, that is n factorial. So 3 factorial is 3 into 2, that is 6. So these are all the possible combination where first T1 comes and then T2 T3, then T2 comes, then T1 T3, then T3 comes, then T2 T1. So these are all the possible 6 combination. So what we have to do is, we have drawn the graph. Now we have to find the in degree of the graph. So what is the in degree? In degree is the number of edges that is directed to that particular node. So we have to see that this is the node and how many edges are directed to this particular node. So if we see here, the in degree for T3 is 2. The in degree, there is no direction, so there is 0, and the in degree for T1 is 1 because there is one directed edge, here there is 2 directed edge, and here there is no directed edge. So we have found out for T1 it's 1, for T2 it's 0, and for T3 it's 2. So once we find the in degree, we have to find that particular node where the in degree is 0. So that would be the first one in the serial execution. So in T2 the in degree is 0, that is the less conflicts are there in T2. So we would be having T2 as the first in the serial execution. Now we will remove T2 from this particular graph. Now here it is T1 and T3. So now the in degree for T3 is 1 and for T1 it's 0. So now it will be followed by T1 and then it will be followed by T3. So this is how we find the serial execution of a conflict serializable graph. So what we have to do is, first we have to draw the conflict graph. Then in the conflict graph, we have to check if there is a cycle or not. If there is a cycle, we can say that that is not conflict serializable. And if there are no cycles, we have to find the in degree for all the nodes which are present in the graph. Once we find the in degree, we have to check that which particular node is having 0 as the in degree. So that would be the first one in the serial execution. Then we have to discard that particular node from the graph, and then again we have to check the in degree of all the other transaction, and we have to follow the serial execution in that manner. So the one possible equivalent serial schedule is T2 followed by T1 followed by T3. So all the executions would be happening first for T2, then T1 and then T3. So let's see if it is helping us to make a serial schedule without any conflicts. So there is T1, T2 and T3. So first T2 operations would be executed. So that is read of A, write of B. So it would be read of A, write of B. Then coming to T1, so it would be read of A, write of A. And then coming to T3, so that would be write of A and read of B. So here we can see the adjacent conflicts which were present earlier are now gone. So this is a conflict equivalent of this particular schedule which is present here. Now, what was the need of this view serializability? So in concurrent schedule, there was a non-serial execution of all the transaction. Now, since there was a non-serial execution of transactions, there was some consistency issue which was lacking in this particular schedule. So just to encounter this consistency issue, we introduced this serializability concept. Now, in this serializability, it makes sure that this non-serial execution get converted into a serial execution. So we find an equivalent schedule in which there is a serial execution. Now there were 2 types of serializability. First was conflict serializability and second was view serializability. Now in conflict serializability, we draw a conflict graph, or you can say precedence graph, in which we see that if the graph has any cycle or not. If the graph doesn't have any cycle, we can say that that particular graph or that particular schedule is a conflict serializable schedule, which means that that particular schedule is serializable. Now coming to view equivalent schedule. So whenever in this conflict graph there is a cycle, so we don't know that if that particular schedule is serializable or not. So because of that reason, we go to view serializable schedule. Now in this view serializable schedule, we find a view equivalent, and in this view equivalent, we check for certain condition, and if these conditions are met, we say that this particular schedule is view serializable. That is why the schedule is serializable. But if these conditions are not met, then we say that view serializability is not there, because of which the schedule is not serializable. So serializability helps us to tell that if a given schedule is serializable or not, or can have a a serial execution or not. So view serializability ensures that the database state seen by transaction in a concurrent schedule can be replaced by some serial execution of those transactions. Now whenever we find cycle in conflict graph, we don't know if our schedule is serializable or not. So we use the view serializability here. So whenever we find the cycle in the conflict equivalent graph, we go to the view serializability to check if the schedule is serializable or not. Now a schedule is view serializable if its view equivalent is equal to serial schedule or execution. So whenever the view equivalent of a given schedule is equal to having a serial execution, we say that this particular schedule is serializable. Now let's see the condition for a view equivalent schedule. So for a schedule to be view equivalent, it should follow the following condition. Now the very first condition is initial read values. So if there are two schedules S and S dash, and S dash is a view equivalent of this particular schedule S, then an initial read of both schedules must be identical. So for example, consider if there are two schedules S and S dash, if in a schedule S, transaction T1 does the initial read for the data item A, then in schedule S dash, transaction T1 should be only doing the initial read on the data item A. So if in schedule S, T1 is the first transaction which is reading the value of A, in schedule S dash, T1 should always be the first transaction which is reading the value of A. That is, if read of operation is being performed on any data item here, it should be performed on the same in the view equivalent schedule. Now coming to the second, that is updated read. So in a schedule S, if Ti is reading B, which is updated by Tj, then in S dash also Ti should be reading B, which is updated by Tj. So consider here there is a read operation which is happening on a given data item which is updated by another transaction. So consider here read of B is happening, and here T2 is updating the value of B. So T2 is updating the value of B, and then the read of B is happening in T3. So the same should be happening in the other schedule, or you can say the view equivalent schedule. So here if you see, T2 is writing the value of B, and here then T3 is reading the value of B. So whenever there is a read-write operation happening, they should be same in both the schedules so that there is no consistency issue which is arised. So if there is any update which is happening on any data item and after that there is a read getting performed, so the execution of transaction in which they are getting performed should be same in both the schedule S and S dash, where S dash is the view equivalent of S. Now coming to the third, that is final update. So a final write must be identical in both the schedules. If in schedule S, transaction Ti is the last to update A, then in schedule S dash, the final write operation on A should be performed by Ti. It's kind of similar to the initial read condition. In initial read, we say that if transaction T1 does the initial read of A, then in S dash also transaction T1 should be doing the initial read of A. That is, if there is a schedule S and if there is a view equivalent schedule S dash, there should be same initial read which is done by same transaction. Now here also it says that if there is a final write which is getting performed in any of the transaction T1, T2 and T3 on a data item X, so the same transaction should be performing that in the view equivalent schedule. So consider if the final write here is happening on data item A which is getting performed on T3. So here also the final write should happen on the data item A and it should be performed by T3. So this should be identical. So there are these three conditions which should be followed. First is initial read, second is updated read, and third is final write. So when these three conditions are met, we can say that this particular schedule or S dash is a view equivalent of S. So here is a question where we have to find the view equivalent of a given schedule. So this is a schedule S and we have to find the view equivalent of this particular schedule. One is we have to find if it is conflict serializable or not. So we have to find if this given schedule S is conflict serializable or not. So we will be drawing the conflict graph, and in this conflict graph first we will be drawing the nodes. So the nodes are all the transaction which is present. So it would be T1, T2 and T3. Then we would be drawing the edges. So edges represent the conflicts. So let's find the conflict. So conflict is always read-write, write-read and write-write when performed on the same data item. And here you can see that there is the same data item on A, it is getting performed. So let's see if there are any read-write, write-write or write-read conflicts. So let's see. So first is read of A. Is there any write of A present in any of the transaction? Yes, it's present in T2 and T3. So we'll just discard this and we'll just draw a line from T2 and then from T3. So let's go to the second, that is right of A. Is there any read of A or write of A present in any of the transaction? Yes, it's present in T1 and T3. Draw an edge from T1 to T2 and then T1 to T3. Now coming to T2. So there is a W of A, that is right of A. Is there any read of A or write of A getting performed? Yes, it is getting performed in T1 and T3. So from T2 there would be a line to T1 and then from T2 there would be a edge to T3. Now coming to T1. Right of A. So is there any read of A or write of A getting performed? Yes, there is a right of A. So T1 to T3 there would be an edge, but it is already drawn, so we won't be drawing it again. Now coming to T3, there is a right of A, but is there any conflicting operation? No. All these values are already discarded, so there are no conflicting operation. So here you can see that from T1 to T2 and then T2 to T1 there is a loop which is being formed, or you can say cycle is being formed. So we can say that this particular schedule is not conflict serializable. Now we will be checking for view serializability. So this step 2 is find the possible number of serial schedules. So how we can find it? That is n factorial. So here the transaction are 1, 2 and 3. So it would be 3 factorial. So what could be the possible combination? So T1 goes to T2 goes to T3. It can be one of the possible serial execution. Then T1 goes to T3 goes to T2. Then T2 goes to T3 goes to T1. Then T2 goes to T1 goes to T3. And then T3 goes to T2 goes to T1, and then T3 goes to T1 goes to T2. So 3 factorial is equal to 6. So here there are 6 possible serial execution. Let's pick up this particular serial execution, and then we would be seeing that if the view equivalent schedule which is formed with this serial execution, that is T1 goes to T2 goes to T3, is equivalent to this particular schedule S. So this would be S dash. So there would be T1, there would be T2 and there would be T3. Now we want a serial execution. So first all the operations of the T1 would be completed, that is read of A and then write of A. Now coming to T2, there is only a write of A. Now coming to T3, there is a write of A. So let's go to all the condition which we told that if there are two schedule S and S dash, they needs to follow this condition for them to be view equivalent. So first one was initial read. So let's see what is the initial read which is happening in this particular transaction S. So here the initial read of A is happening on T1. So T1 is having the initial read in S. Now coming to S dash, T1 is again having the initial read on A. So we can say that the initial read is same in S and S dash. Coming to update read, so let's see that wherever the value of A is getting updated, who is reading the value of A next. So here you can see that the value of A is getting updated here also, but there are no reads which is present after that. And here also the value of A is getting updated in transaction T1, then T2, then T3, but there is no read of A happening. Since there is no read performed after the update, no need to check for the update read. Now coming to the third condition, that is final update. So let's see that what is the final transaction where the value of A is getting updated. So here if you see, T3 is the final transaction where the value of A is getting updated. Now coming to this particular S dash, T3 is again the final transaction where A value is getting updated. So we can say that the final update is happening on T3 in both the schedule S and S dash. So we can say that since the initial read is same, the final update is same, and update read is not valid here because there is no read happening after the update, we can say that S and S dash both are view equivalent. So if the view equivalent schedule matches the condition, it is view serializable. So we can say that this particular schedule S is view serializable because it view equivalent follows all the condition which is needed for a view equivalent schedule. So this is view serializable, and then we can say since it is view serializable, this particular schedule is serializable as well as it can follow a serial execution of transaction. So this is how we find the view equivalent of a given schedule. So before starting with concurrency control mechanism, let's learn about concurrency control. So what is concurrency control? It is a process of managing multiple user access and modification in data simultaneously in shared or multi-user database system. Now consider an example of IRCTC. Now in this IRCTC, at a given time, there are multiple users who are going ahead and booking ticket from themselves. Now here, since there are multiple users who are going ahead and booking ticket from themselves, we can call it a multi-user system. Now here this IRCTC database would be getting updated or modified by multiple users. So we can say that this particular database is a multi-user database or a shared database. So for managing this multiple users and multi-user database, IRCTC uses this concurrency control. So it uses the concurrency control so that it can manage multiple user access and modification in data simultaneously in a multi-user database system. Now how it helps? So the first one is data consistency. So it ensures that the data remains accurate and reliable despite concurrent access. So concurrency control makes sure data is consistent even if there are multiple users who are accessing the website or the database at the same time. Now coming to the second thing, that is isolation. So it maintains the isolation property of transaction so that the outcome of a transaction is not affected by other concurrently executing transaction. Now since there are multiple users who are doing transaction at the same time, so consider user 1 is doing transaction T1, user 2 is doing transaction T2 and user 3 is doing transaction T3. Now as part of this transaction we are doing some operations of read and write. As part of this transaction also we are doing some read write operation. As part of this transaction also we are doing some read write operation. So there should be an isolation which should be maintained between different transactions so that if there is any modification of data which is being made here, this particular transaction doesn't affect from this particular read and write operations which is happening in transaction T1. So there should be an isolation between these three transactions so that the operation of one transaction doesn't affect the operation of other transaction until or unless this particular transaction is committed. Now coming to the third pointer, that is serializability. So it ensures that the result of concurrent transaction is same as if the transaction has been executed serially. So in the concurrent schedule, or you can say in the concurrent transaction, there is a non-serial execution of transactions. So because of this non-serial execution, there is some consistency issues which arises in our database. So serializability makes sure that this particular non-serial execution is converted into a serial execution so that consistency issue is encountered so that our database follows the ACID properties. Now coming to concurrency control mechanism. So we had serializability using which we were telling that if a given schedule is serializable or not, and there were view serializability, conflict serializability which were helping us for the same. Then what was the need of this concurrency control mechanism? So as part of serializability we were only telling that if a given schedule is serializable or not, but as part of concurrency control mechanism we use some techniques to make that particular schedule as a serializable schedule. So here we are using techniques to make a schedule as serializable. Here we were only using techniques to tell if a given schedule is serializable or not. So concurrency control mechanism are techniques used in database management system to ensure that the transactions are executed concurrently without leading to any inconsistency in the database. So whenever there is a concurrent execution, or you can say non-serial execution, there are some consistency issues which arises in our databases. So concurrency control mechanism makes sure that this particular inconsistency is not happening in our databases. Now in serializability we check if a given schedule is serializable or not, but in concurrency control we use certain techniques to make a schedule serializable. So we use certain techniques to make this particular schedule as a serializable schedule. Now why this particular concurrency control mechanism is needed? So there are certain anomalies or there are certain conflicts which arises in our databases. So first is lost updates. So whenever two or more transactions update the same data simultaneously and one of the update might be lost. For example, if two users modify the same record at the same time, the changes made by one user could override the changes made by other. So consider that if there are two transactions T1 and T2, T1 is performing a write operation on A and T2 is again performing a write operation on A. T2 commits, so here the updated value of A is considered 10, here the updated value of A is considered 60. So here the value of A is committed at 60, but after this the T1 also commits, so final value of A updated in our database would be 10. So you can see that there are some inconsistency which is arising and the changes made by one user could be override by the changes made by other user. Now coming to the second, that is dirty reads. So whenever a transaction reads data that has been modified by another transaction but not yet committed, if the first transaction rollbacks, the other transaction will read invalid data. So consider if there are two transactions T1 and T2. As part of T1 I am doing a read of A and write of A. As part of T2 I am reading the updated value of A. So here I have read the updated value of A. So consider the value of A here was 10. After update the value of A was 20. So here the value of A which was read was 20. Now consider at some moment this particular transaction T1 fails. So it will go ahead and roll back all the values. It will go ahead and roll back the value of A to 10. But here the value of A was read as 20. Now this particular value becomes invalid. So that is why dirty reads happen. Now coming to the third one, that is uncommitted dependency, or you can say dirty writes. So when a transaction modifies data that has been read by another transaction, leading to inconsistency if one of the transaction rollbacks. It says that consider if there are three transactions T1, T2 and T3. As part of T1 I am doing an update on A, as part of T2 also I am doing an update on A, and as part of T3 I am doing a write on A. And consider that because of any reasons this particular transaction fails. So since this particular transaction has failed, it will roll back the value of A to its original value, but here we haven't read the value of A. So this particular transaction has done some modification in A, and after this modification has been done, this particular transaction is reading this value. Now this particular value is inconsistent because there has been a failure in T1. So because of the failure in T1, this particular value becomes invalid, and because of that this particular value always become invalid. So there is uncommitted dependency because the transaction haven't committed, and because of the transaction haven't committed, there are some inconsistency which arises in our database. Now coming to inconsistent retrievals, that is non-repeatable reads. So it happens when a transaction reads the same data multiple times and get different value each time because another transaction is modifying the data between the reads. So consider if there are two transactions T1 and T2. As part of T1 I am reading the value of A, as part of T2 I am modifying the value of A, and again as part of T1 I am reading the value of A. So the value of A which is read here and the value of A which is read here would be different. So here you can see that as part of only one transaction, if I am doing two read operations, I am getting modified data. So that leads to non-repeatable reads. Now coming to phantom reads. So it occurs when a transaction reads a set of rows that satisfy a condition, but another transaction inserts or deletes rows that affect the set before the first transaction complete. This results in first transaction reading different set of rows if it re-executes the query. Consider if there are two queries Q1 and Q2. As part of Q2 I am adding or inserting some rows in my DB. As part of Q2 I am reading the number of rows or fetching the number of rows. So if I do this Q2 operation once, I get 3 rows, and if this Q1 operation is also executed at the same time, it will go ahead and add one more row, and after consider 1 second only, if I am again doing this read operation, I'll get 4 rows. So you can see that there are different number of rows which I am getting because of the addition. If consider that this is not addition, this is deletion, and it goes ahead and deletes some of the rows. So first it was 3 rows, now it is 2 rows. So here you can see that there is some discrepancies in the number of rows which I am reading while doing the query. Now coming to the some common concurrency control mechanism. So the first one is log-based protocol. Now as part of this we would be learning about two-phase locking, strict two-phase locking and locking protocols. Coming to the next one, that is timestamp based protocols. So as part of this we would be learning about basic timestamp ordering and Thomas Wright's rule. The third one is optimistic concurrency control, that is OCC. Fourth one is multi-version concurrency control, that is MVCC. Now from semester and interview point of view, this log-based and timestamp based protocols are important, so we would be learning about them in more depth. About optimistic and multi-version, we would be seeing about the definition and what they are exactly, but we won't be going in more depth. So here are some of the commonly used concurrency control mechanism. The first one is log-based protocol. The second one is timestamp based protocols. The third one is optimistic concurrency control. And the fourth one is multi-version concurrency control. So let's start with log-based protocols. So before starting with log-based protocol, let's just revise some older concepts. So in concurrent schedule, there was a non-serial execution happening, and because of this non-serial execution, the consistency was very low. Now for this non-serial execution, we introduced the methods such as serializability and concurrency control mechanism. As part of serializability, we try to see that if a given schedule is serializable or not. As part of concurrency control mechanism, we make the schedule as serializable. So here is the first concurrency control mechanism, that is log-based protocol. So as the name suggests, we are using some kind of logs so that we can achieve serializability and so that we can make a schedule serializable. So here are some types of log. The first log is binary log. So it is a simple mechanism where a data item can either be logged or unlocked. If a thread tries to acquire the lock when it's already locked, it must wait until the lock is released by the thread currently holding it. So as part of binary lock, we can lock or unlock a given data item A. Now coming to the next log, that is shared and exclusive log. So in shared log, it allows multiple transactions to read a data item simultaneously but prevents any of them from modifying it. So whenever we want to perform a read operation on any data item, we can use a shared log, but we can't do any modification. Multiple transaction can hold shared lock on the same data item at the same time. So since it is used for the read operation, and whenever there is a read happening in different transaction, there is no conflicts. So multiple transaction can hold a shared lock on a same data item. Now coming to exclusive lock. So it allows a transaction to both read and modify a data item. When an exclusive lock is held by a transaction, no other transaction can read or modify the data item. So whenever we want to perform a read as well as write operation on a data item, we can use an exclusive lock. Now whenever we are using an exclusive lock in one of the transaction, in next transaction we can't use the exclusive lock on the same data item because there might be some read as well as write conflicts. So in shared lock we are using it for read purpose, and exclusive lock we are using it for read as well as write purpose. So whenever there is a write operation involved, there might be some conflicts such as write read conflict, write write conflict, and read write conflict. So just to avoid all these conflicts, if there is one transaction which is acquiring a exclusive lock, we don't provide exclusive lock to the next transaction. So if there are two transactions T1 and T2, and T1 is having an exclusive lock, when T1 unlocks that particular exclusive lock, we can assign an exclusive lock to T2 for the same data item. So when it is unlocked, we can go ahead and assign the lock. But in shared lock, if transaction T1 is having a shared lock on a data item A, as part of T2 also we can assign a shared lock on data item A, because there is a read operation, so there is no conflict. But here, since write operation is involved, there could be read write read conflicts. So here you can see that there are two transactions T1 and T2. As part of T1 we are giving an exclusive lock, we are performing a read operation on A, write operation on A, and then we are unlocking it. After that we are providing a shared lock on B. So here you can see that there are different data items. So if there are different data items, we don't need to wait for one particular exclusive lock to unlock or release itself. We can provide any shared or exclusive lock to different data item. It is only applicable when the data item is same. So whenever there is a same data item, we can say that there could be some conflicts, but when the data item are different, there won't be any conflicts. So here we have provided a shared lock, we are reading the value of B, and then we are unlocking it. So when we unlock any lock, we can go ahead and provide any shared or exclusive lock in case of an exclusive lock. So when a transaction acquires a shared lock on a data item, other transaction can also acquire a shared lock on the same data item. So if there are two transactions T1 and T2, and T1 is acquiring a shared lock, as part of T2 we can again acquire a shared lock, enabling concurrent reads. However, no transaction can acquire an exclusive lock on the data item as long as one or more shared locks are held. So if there are two transactions T1 and T2, as part of T1 if I am giving a shared lock on A, I can't provide any exclusive lock on A as part of T2 until this particular lock unlock itself, because again as part of exclusive lock I am doing a read as well as write operation, and as part of shared lock I am doing a read operation. So there could be a read write conflict which could occur. So there will be a RW conflict. Now, when a transaction acquires an exclusive lock on the data item, it has full control over the item, meaning it can read and modify it. No other transaction can acquire a lock on the same data item until its exclusive lock has been released. So if there are two transactions T1 and T2, and if T1 is acquiring an exclusive lock on A, T2 can't acquire an exclusive lock on A until or unless this particular lock is unlocked. So if there is an exclusive lock involved, there won't be any shared lock or exclusive lock, and if there is a shared lock, then there won't be any exclusive lock. There can only be a shared lock. So when there is a shared lock, there can be only shared lock, no exclusive lock. When there is an exclusive lock, there can't be any shared or exclusive locks. So shared lock can be present in any number of transactions. For exclusive lock, only one transaction should hold it at one time. So while shared and exclusive locks are vital for maintaining data integrity and consistency in concurrent environments, they can also introduce significant challenges in terms of performance, deadlocks, reduced concurrency, and system complexity. So although they are helping us to achieve serializability to some extent, but there are some issues such as deadlock, reduced concurrency, and system complexity. Now, what are the drawbacks of shared and exclusive lock? So the very first one is performance issue. Managing lock require additional CPU and memory resources. The process of acquiring, releasing, and managing locks can introduce significant overhead. So here we are acquiring a lock of exclusive or shared, and then we are releasing that particular lock. So it can introduce some performance overhead, because of which the performance issues can arise in our CPU as well as in our memory. Now coming to the next pointer, that is concurrency issues. So exclusive lock prevent prevent other transaction from accessing locked data item, which can significantly reduce concurrency. So in concurrency, what we say is if there are two transactions T1 and T2, there could be some interleaved transaction which is happening. But if I am acquiring an exclusive lock in any one of the operation of the transaction, other transaction can't go ahead and access the same data item until or unless the lock is released. So coming to the next point, that is starvation. Some transaction may be delayed if higher priority transaction consistently acquire locks before them, leading to starvation where a transaction never gets to proceed. Consider if there are three transactions T1, T2 and T3. As part of T1, I am acquiring an exclusive lock. It is happening at time T. As part of T2, I am acquiring a shared lock. It is happening at time T dash. And as part of T3, again, I am acquiring a shared lock, which is happening at point T double dash. So here you can see that we are acquiring locks in different transaction, but since in transaction T1 there is an exclusive lock and this lock isn't released yet, so there won't be any lock which would be acquired in T2 and T3, and they will wait for T1 to complete. Consider that T1 completes at time T double dash. There is an unlock happened at time T double dash, and here shared lock on A is being demanded. So it will go ahead and give that particular lock to T3. It will say that your wait time is over, now you can acquire a lock. But T2 was waiting from the long to get the lock for itself, but it is now again waiting because there are some more higher priority operations which are coming into picture. This is how starvation happens in transaction, when transaction may be delayed if higher priority transaction consistently acquire locks. Now coming to deadlocks. So shared and exclusive lock can lead to deadlocks where two or more transactions hold locks that other transaction need. So there could be some deadlocks which could be formed, because consider if there are two transactions T1 and T2, where T1 is acquiring an exclusive lock on A. Now T2 comes in, acquire an exclusive lock on B. This could happen because the data item are different. Now again T1 wants an exclusive lock on B, so it needs to wait for T2 to get completed, and consider that T2 again want an exclusive lock on A, so it needs for T1 to get completed. So here you can see that there is a loop which is getting formed and none of the transaction is ever completing and they are waiting for themselves. So because of this, the deadlock issue happens. We'll be learning about deadlocks in more depth in next set of slides. Now coming to the next point, that is irrecoverable. So if transaction B commits after the lock is released based on a modified value in transaction A which fails after some time. So consider if there are two transactions T1 and T2. As part of T1, I am giving an exclusive lock on A. I am reading the value of A. I am modifying the value of A, and then I am unlocking A. As part of T2, again I am giving an exclusive lock on A. I am reading the value of A and I am writing the value of A, and then I am unlocking it. Consider that this particular transaction T2 goes ahead and commit all the changes in the database. Now in the database all the changes have been committed and it has read the updated value here, and on basis of that updated value it has performed the write operation. But consider that at some point this particular transaction fails, because nowhere we have told that there would be unlock happening when the transaction has committed all the changes. We haven't said that. So there could be a chances that there is some failure which has happened at some point of this particular transaction. So it will roll back all the operation and all the changes which was done as part of this transaction, but this particular transaction has read the value which was modified as part of T1, but now T2 is having an invalid value and that is already updated in our database. So this particular transaction can be recovered, but this particular transaction can't be recovered. So there is irrecoverability. Now what is this deadlock? So it is a situation when two or more transactions wait for one another to give up the locks. So here you can see that there is a resource R1 which is assigned to a process P1. Now P1 is waiting for R2 and R2 is assigned to P2 which is waiting for R1. So here you can see that there is a loop which is getting formed because P1 is dependent on R2, R2 is dependent on P2, P2 is dependent on R1 and R1 is dependent on P1. So there is a loop and there is a deadlock which is getting formed. So we saw that in the shared and exclusive lock there were some drawbacks. So because of this we introduced the two-phase locking. Now what is this two-phase locking protocol? This protocol ensures serializability by dividing the execution of a transaction into two distinct phases. First one is a growing phase. A transaction can only acquire locks but cannot release any. This phase continues until the transaction has obtained all the lock it needs. And coming to the shrinking phase, so after the transaction releases its first lock, it can no longer longer acquire any new locks. During this phase, the transaction releases all the locks. So there are two phases, growing phase and shrinking phase. In growing phase, they can go ahead and acquire any kind of lock they want, and in shrinking phase, they have to unlock all the locks and they can't acquire any lock. So because of which the transaction can achieve serializability and consistency in the given schedule. So let's see how it happens. So here are two transactions, T1 and T2. As part of T1, we are acquiring an exclusive lock on A. So we can say that T1 is right now in a growing phase. So it is going in a growing phase. So there is a read of A, write of A happening. Now transaction T2 comes. But since T1 is right now in a growing phase and T2 is not in a growing phase, there won't be any locks which would be assigned to T2. It will wait for this one to have in a shrinking phase and unlock all the locks. Now coming to here, there is a shared lock acquired on B, there is a read on B. So till here there is a growing phase which is happening because all the operations of the transaction are only acquiring the locks. Now there is a unlock of A which is happening, which is for this exclusive lock, and then there is a unlock of B which is happening, which is for this particular shared lock. So this particular state we can call as shrinking phase, and this particular phase we can call as growing phase. So now there is a growing phase of T1 and then there is a shrinking phase of T1, and since the shrinking phase of T1 is achieved, we can go ahead and acquire a shared lock on A present here because right now it is unlocked. So you can see that when a transaction acquires a growing phase, it will go ahead and acquire locks in that particular growing phase. It won't go to another transaction and give any kind of locks until or unless there is a shrinking phase which has happened for all the locks which is present here, and then they can go ahead and give the shared lock or exclusive lock in another transaction which are waiting for them to get completed. So in this way we can achieve the serializability and consistency, because here you can see that first all the operation of transaction T1 is getting completed, only then the T2 one is starting. So T1 is getting completed first and then the T2 is starting. So there is a serializability which is achieved here. Now let's see the advantages and disadvantages of 2PL, that is two phase locking. So first one is it guarantees that the schedule of transaction will be serializable, meaning the results of executing transaction concurrently will be the same way as they were executed in some serial order. So if there are two transactions T1 and T2 and there are some operation which is happening concurrently, consider read of A, write of A in T1, then there is a read of A in T2, then there is a read of B in T1, and then there is a write of B in T1. So as part of 2PL, there will be two phases, growing phase and shrinking phase. So first it will start with the growing phase. It will acquire an exclusive lock on A. There will be one more exclusive lock on B. So it will acquire all the locks in the growing phase. Now there will be a shrinking phase where it will unlock all the locks. So it will unlock A and it will unlock B. But since T2 has a read operation, it will wait for this particular exclusive lock to get released. Only then it can acquire a lock. So the shared lock on A in T2 will wait for this particular exclusive lock on A to get completed or get unlocked. Only then the transaction of T2 will start. So here you can see first the transaction of T1 is getting completed, then only T2 is getting started. So there is a serial execution which is established. So there is a serializability. Now by ensuring that the transaction are serializable, 2PL helps to maintain data integrity and consistency, which is critical in environments where data accuracy is essential. Now coming to disadvantages, deadlocks, starvation and cascading rollbacks are still there. So consider if there are three transactions T1, T2 and T3. As part of T1, we are acquiring an exclusive lock on A. As part of T2, we are acquiring an exclusive lock on A. And as part of T3, we are acquiring a shared lock on A. Now consider that this particular has come to its shrinking phase and there is an unlock which has happened. So this one was waiting for this unlock to happen so that it can acquire an exclusive lock, and this was waiting for this one to complete so that it can acquire a shared lock. Now consider at some moment of time this particular transaction fails. So it will go ahead and roll back this particular transaction, but since this and this transaction was dependent on the changes which was done as part of T1, so this will also go ahead and roll back and this will also go ahead and roll back. So there will be a cascading rollback which would be happening because one of the transaction has failed, another transaction had some dependency on this particular transaction T1. Now transaction must wait for the locks to be released by other transaction. This can lead to increased waiting time and lower the system throughput. So here you can see that as part of T2 we wanted to do a read operation, but we need to wait for all the exclusive locks and shared locks which has been assigned in this transaction to get released so that we can acquire any locks and we can proceed with our transaction. So here you can see that the waiting time is more. Now coming to the third one, in case of a system failure, recovering from a crash can be complex, because consider that if at some point this particular transaction failed and this particular transaction was dependent on some of the values which is present in this transaction, so we can't go ahead and roll back the committed changes which we have done as part of other transactions. So in shared and exclusive lock, there were a couple of disadvantages which is taken care in two-phase locking, like serializability is achieved here, concurrency is achieved here, data integrity is achieved here. But there were some disadvantages like irrecoverability, starvation, deadlocks, and cascading aborts, which is newly introduced, is still persisting here. So for this, we have a stricter version of 2PL, that is strict two-phase locking. So what is the strict two-phase locking? A stricter variant where exclusive locks are held until the transaction commits or aborts. So as part of exclusive lock, we do a read as well as write operation, and as part of shared lock, we only do a read operation. So what was happening is, consider in one transaction there is an exclusive lock which is present, there will be a write operation which would be present, and because of this write operation, if another transaction is reading anything which is modified here, and what if this fails, there will be an invalid update into our database. So because of which it says that the exclusive locks are held until the transaction commits or abort. So this particular transaction should commit or abort, only then the unlock of this particular exclusive lock would be happening, so that if there is any modification which is made as part of a transaction T1, T2 shouldn't read any invalid value. If it's a commit, it will go ahead and read the valid value which is present in the database. If this is a abort, it will go ahead and roll back to its original value. So at this case, there won't be any dirty read problems which would be happening. So this helps prevents cascading rollbacks, where one transaction rollback causes other transactions to roll back. So here we are only unlocking it or releasing the lock once the transaction is committed or aborted. So there won't be any cascading rollbacks which would be happening in different transactions, because there were no strict rules for any of the lock that when they can unlock themselves. But as part of strict 2PL, we says that if there is any exclusive lock, it would only unlock itself once it commits or abort its operation. So the advantages are it prevents the cascading aborts. The second advantage is it ensures strict serializability. So there will be a strict serializability which would be ensured, because there won't be any invalid data which is getting updated in our database. So the consistency is more here. Now coming to the disadvantages. So since write locks are held until the end of transaction, other transaction may be blocked for extended periods. So since there is an exclusive lock which is happening in transaction T1, it will only unlock itself once it commit all the changes in the database. So there might be some time which should be taken by transaction T1 to commit all the changes. Till then, T2 would be waiting for a shared lock which needs to be acquired only when the T1 is unlocking the lock. So once T1 is unlocking the lock, only then T2 can acquire a shared lock. So the wait time will be more. Now coming to the next point, that is transaction may experience longer wait time to acquire the locks. So transaction may experience some longer wait time to acquire the locks. Now the third one is deadlocks and starvation is still there. So deadlock and starvation is still not encountered as part of strict 2PL, because again consider as part of T1 we are having an exclusive lock, as part of T2 we are having a shared lock, as part of T3 again we are having an exclusive lock, as part of T4 again we are having a shared locks. So these all locks needs to wait on each other to unlock, so that they can start their execution. So there still be deadlock which would be happening and a loop which would be happening, because all the other transactions are interdependent on each other for them to be unlocked. So here we can see that again there are some disadvantages which are still persisting. So there is one more stricter version of strict two-phase PL, that is rigorous two-phase PL. So what is this rigorous two-phase locking? So it is an even stricter version where all the locks, shared and exclusive, are held until the transaction commits. So 2PL, it says that the exclusive lock should only unlock themselves when they have committed or aborted the changes. But as part of rigorous 2PL, it says that exclusive lock as well as shared lock should commit or abort the changes, only then they can go ahead and unlock themselves. So the lock are held until the transaction commits or aborts. Now what are the advantages? Since all the locks are held until the end of transaction, the system can easily ensure that the transaction are serialized and can be recovered. So since there are locks which is getting held in both exclusive as well as shared lock, so there is a guarantee of serializability as well as recoverability. Now it prevents the cascading aborts and dirty reads. What are the disadvantages? So the performance bottlenecks are there. Increased transaction duration, because earlier they were only hold on the exclusive lock, but now the hold is present on the exclusive as well as shared lock until or unless they commit or abort. So there is an increased transaction duration. Third point is deadlock and starvation is there. So we can see that deadlock and starvation is something which is getting persisted for all the 2PL, two-phase locking, strict two-phase locking, rigorous two-phase locking. So again there is one more locking protocol, that is conservating two-phase locking. So conservative two-phase locking or you can say static two-phase locking, is a variant of a standard two-phase protocol that aims to prevent deadlocks entirely by requiring a transaction to acquire all the lock it needs before it begins its execution. So what it says that all the transactions should acquire all the locks before even the transaction starts its execution. So if the transaction is unable to acquire all the required locks because some are already held by other transaction, it wait and retries. The transaction only starts execution once it has successfully acquired all the necessary locks. So once a given transaction has acquired all the locks which is needed as part of an operation which is present in the transaction, only then it will start its execution. Until or unless then it won't start its execution and it will wait. So consider if there are two transactions T1 and T2. As part of T1, we are doing a read operation on A, write operation on A. As part of T2, we are doing a read operation on B, write operation on B. As part of T1, again we are doing a read operation on A, write operation on A. As part of T2, we are doing a read operation on B and write operation on B. So before even the transaction start executing, it will acquire all the locks. So here it will need an exclusive lock on A. It will need an exclusive lock on B. So before the transaction start, it will acquire all the locks. So here T1 has acquired exclusive lock on A and exclusive lock on B. So since T1 has acquired the exclusive lock on A and exclusive lock on B, T2 can't go ahead and acquire any exclusive lock because T1 has already acquired all the locks which is needed for T2. And T2 can't start its execution even if one of the lock which is needed by T2 is not present, right? So first T1 will start all its execution, only then T2 can go ahead and acquire any locks and start its execution. So because of this, there won't be any deadlock scenario which would be present, because since a transaction never starts executing until it has all the lock it needs, deadlock cannot occur because no transaction will ever hold some locks and wait for other. So here T2 won't be holding any locks even though it requires an exclusive lock on A and exclusive lock on B. It needs to wait for this particular transaction to get completed. Only then T2 can go ahead and start its execution and acquire the lock. Here T2 has not even started its execution, then how it can go ahead and acquire a lock, right? So there won't be any deadlock situation which would be present here because T2 can't acquire any lock because all the locks have been acquired by T1 and it needs to wait for them. So in this scenario, deadlock cannot occur because neither T1 nor T2 starts its execution until it has all the lock it needs. Now coming to the next concurrency control technique, that is timestamp based protocol. So it assigns a unique timestamp. So whenever there are two transactions T1 and T2 and they start at any instant T, or you can say T dash, so it gives a unique timestamp to the transaction whenever they start its execution or their operations. So every transaction is assigned a unique timestamp when it enters the system. It is used to order the transaction based on their timestamp. So we can order the transaction that T1 started first, then T2 started, or we can also order their operation that read of A started of T1 first, then read of A of T2 started. So all these operation and all these transaction we can give a timestamp. So there are two important timestamps for each data item. First one is read timestamp, second one is write timestamp. So the last timestamp of any transaction that has successfully read the data item, that is RTS. So consider if there are two transactions T1 and T2. As part of T1, I am reading a value of A, writing a value of A. As part of T2, I am reading a value of A. So the last read operation on data item A happened on T2. So we can say that the last read operation happened in transaction T2 at particular timestamp T dash. So that is the RTS. Now coming to WTS, consider that it is doing a update on A and here also it is doing a update on A. So we can see that the last update on A has happened in T2 at timestamp, you can say T double dash. So WTS of this is T double dash and RTS of this is T dash. So we give the latest of the read and the latest of the write timestamp. Now transaction with smaller timestamp are called as old transaction. Transaction with larger timestamp are called as young transaction, because consider that if there are two transactions T1 and T2, now T1 started at 7 p.m. and T2 started at 7:10 p.m. So we can say that this particular one would be having a larger timestamp and it would be having a smaller timestamp. So we can say that this particular transaction is an old transaction and this particular transaction is a young, or you can say a fresh transaction. Here are some rules for the timestamp based protocols which help us to tell that if there is a transaction, as part of that transaction, if there are any operation that should be executed or that should be rejected. So here is a RTS, that is read timestamp of A, WTS, that is write timestamp of A. So consider if the transactions are getting performed on a data item A. So first one is check the following condition whenever a transaction Ti issues a read operation. So whenever there is a read operation which is issued by a transaction Ti, what should we check? So first one is the write timestamp of A should be greater than the timestamp of Ti, then the operation is rejected, that is rollback. If the write timestamp of A is less than or equal to the timestamp of Ti, then the operation is executed, and we set the read timestamp of A as the maximum of read timestamp of A and the timestamp of transaction Ti. Now coming to the second pointer, check the following condition when the transaction Ti issues a write operation. So the first one is if the transaction Ti is less than the read timestamp of A, then the operation is rejected, that is roll back the transaction Ti. If transaction of Ti is less than the write timestamp of A, then the operation is rejected and Ti is rolled back, otherwise the operation is executed, and we set the write timestamp of A to timestamp of Ti. Now again, I know that this particular rules would be sounding very confusing to you. You won't be even understanding that what is happening here. So I'll just give you a small trick which you can keep in mind so that you can know that if there are two transactions T1 and T2, then what all operations should be executed or rejected. So I told you about old and young transaction, how we distinguish between old and young transactions. So consider if there are two transactions T1 and T2, and if the timestamp of T1 is less than the timestamp of T2, we can say that T1 is an old transaction and T2 is a young transaction. Now consider if as part of T1 and T2 we are performing some operation. So since T1 is an old transaction, we assume that T1 should be completed first, only then T2 should be completed. So there would be a serial execution that T1 should be completed first, only then T2 should be completed. Now consider that as part of T1 I am doing some operations, and as part of T2 also I am doing some operations. So here there are no issues because T1 is getting completed first, only then T2 is getting completed. But consider if there is a use case where T2 operation is starting first, and then after T1 operation, either read operation or write operation is happening, although T2 started at a later point. So whenever the older one has done all the operations and then younger one has started its operation and older one is getting completed, there is no issues. But when the younger one has done all the operations and then older one comes ahead and does some of the operations, then there would be a rollback. So let's assume that there are two transactions T1 and T2. Suppose the transaction T1 has entered the system at 7 p.m. and transaction T2 has entered the system at 7:05. So T1 is the old transaction and T2 is the young transaction. Now then T1 has a higher priority, so it executes first and it enters the system first. So T1 will be executing first and then T2 would be executing. So it will be T1 goes to T2, that is a serial execution where T1 operations is completed and then T2 operation is getting completed. So how we can see that if there would be any rollbacks which would be happening? So if the younger one has done a read or write operation, so younger one has done a read or write operation and older one wants to do a read or write operation, then that is a rollback case. If younger one has done any read or write operation and older one wants to do any read or write, so there should be a rollback. So you can just remember in this way that if younger one is performing any operation and then the older one comes in and perform any of the operation, there should be a rollback. But if older one is performing any operation and then younger ones come, then there is a no rollback. So here you can see that there are two transactions T1 and T2. T1 is old, T2 is younger. So T1 is performing operation, T2 is performing operation, no issues. T1 is performing a write operation, T2 is performing a read operation, no issues. T1 is performing a write operation, T2 is performing a write operation, no issues. Because we are expecting that T1 would be completed first as it has entered the system first, and on the basis of priority T1 should be completed. So this is how this timestamp based protocol works. So you just need to remember that if the younger one does some transaction and after that the older one comes ahead and does some transaction, they should roll back. But if the older one is doing any transaction and after that the younger one is doing, there shouldn't be any rollback cases. So this is all about the concurrency control mechanism. Now the first question which comes in mind is that why do we even need to learn about this database recovery management? So it involves strategies and processes to restore a database to a consistent state after a failure or crash. So whenever there is a failure or crash, we need some methods or management so that we can recover our database. Now what are the types of database failure? So the first one is transaction failure. It occurs when a transaction cannot complete successfully due to logical errors, or you can say system issues like deadlocks. So whenever there are some logical errors or system issues like deadlocks, we can face some transaction failure which could happen in our databases. The second one is system failure. So it occurs when the entire system crashes due to a hardware or software failure, leading to loss of in-memory data. We have seen at certain times our laptop get turned off automatically or our computer system get turned off automatically. So there could be a system failure which could happen in our laptops or in our computers, which could lead to loss in memory of the data. So we need to recover from this particular failure. Now coming to the next failure, that is media failure. So it occurs when the physical storage, that is hard drive, is damaged, resulting in data loss or corruption. So whenever there is a failure in a physical storage, or you can say hard drives, it results in the corrupting of data, because of which there is a data loss. Now we need to recover from all these failures. So what are the recovery methods we can follow? So first let's see about the recovery phases. So the first phase is analysis phase. It identifies the point of failure and the transaction that were active at that time. So it will identify that at what point the failure happened and what were the transactions that were active at that particular instant of time. Now coming to the redo phase, so it reapplies the changes from the committed transaction to ensure that the database reflects all completed operation. So whenever there is a failure which has happened as part of a transaction, it goes ahead and roll back that particular transaction. So as part of rollback, it will go ahead and roll back all the operation which has happened as part of this particular transaction. So it reapplies all the changes from the committed transaction. As part of rollback, it will go ahead and reapply all the changes from the last committed transaction which was successful to ensure that the database reflect all the completed operation. Now the third phase is the undo phase. It reverts all the effects of incomplete transaction to maintain the consistency. So here in the rollback, we are rollbacking all the operations which needs to be performed as part of T1. So let's learn about the recovery techniques. The first one is backup and restore. So whenever we take the regular backups, we ensure that the data can be recovered to the last backup which has been taken. So full, incremental and differential backup are the common types of backup. Now the second one is logging. So we keep a record of all the transaction, that is transaction logs. The write ahead logging or WAL protocol ensures that the logs are written before any changes are applied to the database. So whenever there is a transaction happening, if it does any read or write operation, it is getting saved in our transaction logs, and once all the changes have been committed to the database, it goes ahead and delete the transaction log. But if the changes are not committed to the database, we have the transaction log, and using this we can recover our database. Now the third one is shadow paging. So what is shadow paging? It maintains two copies of the database pages. One is the updated one and the other remains unchanged until the transaction commits. So if there is one database D, it will make a copy of that particular database D dash, and in that particular database D dash we have all the last changes which were saved, and we'll be doing all the operations on D. Now D dash would be having all the changes which were saved at the last time. So even if there is any failure occurred at D, it can go ahead and recover all the data which has been lost as part of D's failure. So these are all the techniques which we oftenly follow whenever we have any failure in our databases. So this was all about this video. I hope you like this video. So if you like this video, please hit the like button. If you're someone who is new to my channel, can go ahead and watch out the tech content first, and if you find it useful, can go ahead and subscribe. Also, if you have not followed me on my social media handles, you can go ahead and follow. The links are in the description. Till then, take care, keep learning, keep growing, keep smiling.